Hello, everyone. Welcome to the last day of lecture of the ICMAM Latin America Conference on Algebra, Combinatorics, and Number Theory. For the first talk, we have Luis Núñez Betancourt as host. He works at the Center of Research in Mathematics in Mexico and is member of the scientific board of this conference. And whatever you want, you can start, Luis, please.
Okay, well, thank you, Erika. It is an honor for me to introduce the first speaker of the day. He is Professor Ezra Miller. He was an undergrad student at Brown, then he obtained his PhD from Berkeley. Ezra is professor both in mathematics and in statistical science at Duke. He studies and solves problems coming from everywhere. Just to mention a few, geometry, algebra, topology, combinatorics, statistics, probability, and among others. His research has touched other sciences, such as biology, chemistry, and computer science. He also wrote a very influential book together with Bart Stumpfels on combinatorial primitive algebra. And I know that Ezra has visited Latin America multiple times. Last count, it was like 5 times to Mexico, but also he has visited other countries in Latin America. And I'm very happy he's visiting again, even if it is virtually. Well, thanks, Ezra. Go ahead.
All right, thank you for the introduction. Thank you for the invitation. It's my pleasure to speak here. I'm going to talk about some advances in multigraded algebra. What this means is well, we'll talk about what multigraded algebra is, but it's going to be connections to lots of other areas as well, just like Luis was just saying. So, why is that not going? What am I? There, my slides are not advancing. Okay. So here's an outline of the talk. I don't know why it's so light and gray, but there it is. I'll start off from telling everyone what multigradings are. We'll talk about some multigraded homological algebra, toric geometry, and then we'll proceed into more modern things like real exponents and non-commutative toric geometry. I'll talk about a syzygy theorem, which is some homological algebra, and then connections with persistent homology, and then free resolutions of monomial ideals. So this is multidisciplinary work, and it involves researchers of all sorts. Researchers from there's at least one from industry here, although this was a graduate student at UNC when we were working on this stuff together. But they range from undergraduates to postdocs to faculty, and as a result, the mathematics is uneven in level, and you'll find this talk to be uneven in level. So there will be times when maybe you're looking at something and maybe it's not quite clear what I'm talking about. Wait 5 minutes, and it will get more elementary again, and you'll be back on board. So what is a multigrading? So first, what is a polynomial? A polynomial in n variables over a field k is a finite linear combination, and it's just a sum of monomials with coefficients. This is something that I assume everybody has seen before, but at the very least I need to fix some notation. So here the monomials, these are multivariate polynomials. So here the exponent vectors, they occur in the natural numbers to the n. So there's just lists of natural numbers, that's non-negative integers. And x to the a is just a product of x1 to the a1 up through xn to the an. And the set of all these things forms a ring called the polynomial ring. That just means you could multiply them, add them, and subtract them. Now this ring k join x1 through xn, this is a familiar object, but I want to think of it as taking yes. Is there a question?
Sorry.
Okay, so I want to think of it as taking the set of exponent vectors. The set of exponent vectors is closed under addition, and it forms what's called an affine semigroup. So here the affine semigroup is n to the n. You see the only difference here is I've made the n to the n purple. But more generally, you can take any affine semigroup. So this is going to be, you take a set of non-negative, so you take a set of integer vectors inside of z to the n. These integer vectors are a1 up through ad. And then you just take the cone that they generate in some sense. You just take all sums of them, all non-negative sums, and you get an affine semigroup ring. So what does the picture look like here? So instead of taking the entire positive quadrant in the plane, which would give me all monomials in x and y, I could take all the monomials that sit inside of this cone here, and then that's going to give me an affine semigroup ring. I just look at the ring that has a basis given by the monomials only that lie in this cone instead of lying in all of the positive quadrant. Three-dimensional example would be if I took the cone over a square like this, then I could take all the lattice points that sit inside of this cone over a square, and that would give me an affine semigroup ring. So these are, they kind of feel like polynomial rings, but they're not sort of the right-angled orthants that you're used to seeing. So a multigraded module over this affine semigroup ring is it's a family of vector spaces indexed by the lattice here. So here we have z to the n. We have a family of vector spaces. This is a vector space indexed by the element b in z to the n. So this is just, think of it as if you think of it as sort of sitting on top of this picture, it would just be like drawing, it'd be like placing a vector space on each of those dots. That's all it is, placing a vector space on each of those dots. And if you have a monomial x to the a, that is actually one of these dots, but you should think of it as one of these, vectors. So a vector here inside of this, that's pointing from 0 to the lattice point, then that vector tells you how to shift. So if you take the vector space that sits at a point b, then you can multiply it by x to the a, and what that does is it shifts it from b up to a plus b. So it just sort of shifts it, everything up and to the right like this. So multiplication by this monomial x to the a shifts everything up and to the right by a. So examples would be the affine semigroup ring itself. That's just k join q. So that's just, again, there's a one-dimensional vector space sitting at each of these lattice points, right? One-dimensional vector space sitting at each of the lattice points. A monomial ideal, that would be what if you have a set of these lattice points that's closed and they're going up. So the picture there looks like this. Here is the monomial ideal. This is the monomial ideal itself. It's the set of lattice points that sit sort of above this staircase, like this. Or you could take, so here's a three-dimensional version. Here's sort of a fancier picture that has a minimal free resolution drawn on it. And you could take the quotient k join q modulo I. So that would give you all the monomials underneath the staircase down here like this, right? So then you get all these lattice points, and that gives you a module. And so if you try to pass from, for instance, from this lattice point and you try to move up in this direction, then that just goes to 0 in the quotient. That's what the quotient by the monomial ideal says. But if there are any questions at any time, please feel free to ask. You can put it in the chat, or you can ask out loud as far as I'm concerned, but I don't know what the technicalities of that are. Okay, so let's see. I need to get back to my. Okay, so this talk is split into 3 parts. Roughly, it's really 2 parts. Then I'm going to review some history, and then I'll review some what's going on currently. And then I'll give you a little view into what might happen in the future at the end. Okay, so sorry, I'm just looking at the question window. Okay, so multigraded homological algebra. So this is it's got a history that dates back maybe 60 years, something like this. It dates back longer than that, but sort of explicitly, people were thinking about multigraded algebra maybe starting in the 60s and 70s. So Kaplansky in the early 60s wrote down problem lists for his students, and these things are unfortunately not published. But I had the honor to work with one of Kaplansky's students, Jack Egan, and he told me about these problem lists. And one of them was to find a minimal free resolution, was to construct a free resolution of any monomial ideal I. So this is an exact sequence where you take a free module and you surject onto I. You take a free module here and you surject onto I, then you take a free module and surject onto the kernel of that map. The map from here to here has a kernel, and you want to surject onto that, and so on and so forth. And you keep doing this. And it's a basic theorem from commutative algebra that over a polynomial ring, this process always stops. The Hilbert-Syzygy theorem says that you only have to go finitely many steps before it stops. So Hochster and Stanley and Reisner in the 1970s drew connections to simplicial topology, and we'll see some of those very shortly. You'll see how you get simplicial complexes out of monomial ideals. And then they connected these things to
Es álgebra homológica.
Question? I heard someone say something.
No, I'm sorry.
Okay. Connections to algebraic things like Cohen-Macaulay criteria, or to homological things like local cohomology computations. Goto and Watanabe in 1978 have this paper on graded rings 2, z to the n graded rings, where they write down multi-graded complexes and resolutions like free, flat, and injective resolutions, and everything is explicitly multi-graded in the form that I just told you on the previous slide. There have been many textbooks on this kind of material. Stanley in 1983 has his little green book, this Combinatorics and Commutative Algebra book. And there was Brunson Herzog maybe about 10 years later, and then a sequence of textbooks after that, all about multigraded commutative algebra and relations to monomial ideals and determinantal ideals and toric ideals and these kinds of things. So Kaplansky's problem, let me tell you about Kaplansky's problem about monomial ideals. So let's fix a monomial ideal inside of a polynomial ring. So what I mean by that is just an ideal generated by finitely many monomials. So the generating set is just some power products x, x to the a1 up through x to the an. And Kaplansky in the early 1960s posed the problem of finding a minimal free resolution of I. So the combinatorics that comes in here is called the Koszul simplicial complex KB of I, and its definition is sitting over here. It's the set of square free vectors that when you stand at a monomial and look back, you want to see when you're in I. Okay, this is best conveyed by giving a picture, and here's the picture. So if you stand at this lattice point over here, let's say this blue one, and you can ask the question, all right, when I'm standing there, let me look backwards in, say, this direction or that direction or that direction. Let me look at which directions I can look back and stay inside the monomial ideal. So remember, the monomial ideal is the stuff that's closer to you. The monomials outside the ideal are the ones that you can't see that are under this staircase. So you've got this staircase sitting here. You've got this, oops, that's not what I wanted. You've got this staircase sitting here. And you want it, so the monomials under the staircase are the ones that are not in the ideal. The monomials that are above the staircase, those lattice points that are above the staircase, those are the ones that are in the ideal. And so, for instance, this blue one is, so this black one, for instance, is a minimal generator of the ideal. So this is the monomial x times y. This black one up here is the monomial just z. That's the generator over here. And then there's a monomial here, y cubed. Those are the generators of the ideal. And if you stand at, how do you know that you have a minimal generator? Because if you stand there and try to go backwards, that is subtract a vector, then you always end up underneath the staircase. On the other hand, if you're at a blue point, like this blue point, then when you go backwards, you can go down in the z direction and you'll stay outside of the ideal. So there's a generator beneath you. You can go back in the 1, 1 direction, sorry, the 1, 1, 0 direction, that is back in x and back in y, and you'll still be in the ideal. But if you try to go back by 1, 1, 1, that is down in all 3 directions, you'll be under the staircase. So this simplicial complex is what you get by looking at which square free vectors you have that keep you above the staircase. Standing at this red point, you can go backward by any vector except for the vector 1, 1, any square free vector except for the vector 1, 1, 1. And all the other vectors, all these red ones, keep you inside the ideal. So if you go back in any of these other directions, down like that, or down in this direction, or down in that direction, or down in that direction. Okay. So Hochster's formula says that if you look at the minimal free resolution, then the dimension of the vector space that occurs at the ith stage in the minimal free resolution in degree B is the I minus first homology of this vector space, of this simplicial complex. So at this blue simplicial complex, you want to know how many free modules have their generators there. It's the dimension of the homology of this simplicial complex. I guess depends on which homology to which free module you have. So that means the Betti numbers are the dimensions of this homology. Actually, the Tor itself is this more natural way of computing those dimensions, but the Betti number, that's just counting the number of summands, is the dimension of this homology. Now there's a grading in the minimal free resolution, and I'm going to go through this in a substantial amount of detail. So this is what the free resolution looks like. It's just a complex of free modules. So this counts minimal generators. These correspond to first syzygies, second syzygies, and so on. So the fact that you have an n to the n grading in this case tells you that each free module is a direct sum like this. Now, I know that this direct sum looks very complicated. And one of the disadvantages of giving a talk online as opposed to on a blackboard is it's all up there at the same time, and that makes it hard to parse. So what I'm going to do is I'm going to take it apart bit by bit and then tell you what these things mean. So this is just a free module generated in degree b. So this is the same thing as saying the monomial ideal generated by x to the b. So it is just a free module of rank 1 whose generator sits at the lattice point b. And so you should think of it as a positively, you think of it as a quadrant that's that looks like this, where it's this quadrant over here, and the smallest point in there is b. That's how you should think of this thing. Okay, now we have some number of copies of this, and so that's going to be beta IB. That's how many copies of this module we have, and the I over here is telling you which homological degree it's in. So that's the I corresponding to where along this direction you are. Right? I tells you how far this way, B tells you how far you are in the lattice points over here. Okay, and then beta IB tells you how many copies of this thing you've got. And then what you do is you take the tensor product with this homology. What does that actually mean? Well, what you're really saying here, so this is the dimension of the homology. That's what's written over here, that dimension of the homology. That's this beta IB. But another way to say that this vector, that you have this many copies, that you have sort of this many copies of this free module, is to just take the tensor product with this natural vector space. And that's what this thing is. So you take the tensor product with that vector space. That's more or less telling you take beta IB many copies of that free module. And then Fi plus 1 is just the direct sum over all choices of where that lattice point's at. Okay, so let's simplify our notation by taking this this whole big expression and just calling that Fi plus 1b. Okay, so if you wanted to write down a map from the I plus first free module generated in degree b to the ith free module generated in degree a, then it's enough to take the generators of this free module, because this free module has a basis, and this free module has a basis. And what you want to do is take the generators of the basis of this one and tell you and say where they go in terms of the basis of this one. And the way to do that is to take a map on homology from the homology of this Koszul simplicial complex to the homology of this Koszul simplicial complex. And you'll see that this is Hi of some simplicial complex. This is Hi minus 1 of some other simplicial complex. There's no natural topological map that does this. It's not like you look and go, oh, that's just the map induced by some inclusion or something like that. This is some weird map between homologies of simplicial complexes, and Kaplansky's problem comes down to finding what those maps are when A is less than B to give you the induced maps on a free resolution. So this is what Kaplansky's problem said. And there, as I said, all these papers and textbooks, there's what do we really want out of Kaplansky's problem? We want it to be universal. We want it to work for all monomial ideals. We want it to be canonical in the sense that we haven't made any choices as to what the maps in the free resolution are. They should be given to us without us having to choose anything. They should be closed form. I want to be able to write down a formula for it. I would like that formula to be combinatorial. And of course, I want the resolution to be minimal. So I want the number of generators in each degree to be as small as possible. So there are hundreds of papers on this stuff. If you look up free resolution of monomial ideal in MathSciNet, you get literally hundreds of papers. I don't know whether it's 500-600 papers, lots and lots of papers. Here's just a sample of them. Taylor's paper in 1966, Taylor was a student of Kaplansky. Her resolution is beautiful, but it's not minimal. Nubesnik did so sort of computational type resolutions. They're not minimal or canonical. There's all sorts of examples, and you can just look through these. I have a detailed reference list at the end if you want to see what the actual references for these things are. But there's lots of ideas. You could try to make resolutions that are sort of symmetric, right? So that would be something like these polyhedral Hall resolutions. You can make very nice symmetric resolutions, but they're not necessarily minimal. When I say symmetric, I mean they respect the symmetry. If your ideal has symmetry, they respect that symmetry. You can do example. There are lots of examples that are minimal in certain special cases, like when the ideal is generic. There are connections with topology, shelvable monomial ideals. You can look at order complexes. There's all sorts of connections to combinatorics and homological algebra here. Well, this is what the history of Koplansky's problem looks like. Hundreds of papers with lots of interesting ideas connecting combinatorics to commutative and homological algebra. So now let me switch gears and talk about toric geometry, because remember I introduced semigroup rings. These are like polynomial rings, but they allow cones instead of instead of just the right-angled orthants. And so a semigroup ring corresponds to an affine toric variety acted on by an n-torus. Now I'm not going to go into a lot of detail about what an affine toric variety is, but I'm going to try to give some feel for what they sort of look like when you try to work with them. So the first example, though, is a polynomial ring in n variables, and its spectrum is just c to the n. So this is saying so the point is that the polynomial ring is functions on some space. What space is it the functions on? These are the polynomial functions on a vector space c to the n. So c to the n is the affine toric variety associated to this affine semigroup n to the n. That's the idea there. So now in general, a toric variety comes from a family of semigroup rings indexed by a polyhedron. I am not going to make that precise, but I will give you an example to indicate what's going on. So this is 5 affine semigroups glued pentagonally. The point is you've got this red semigroup down at this corner, and you could think of the affine semigroup ring for that semigroup if you'd put this point at the origin, or you could put this yellow semigroup at the origin by putting this black point at the origin. You get that yellow semigroup, and it points in kind of a different direction. And this green semigroup points in yet another direction if you put this point at the origin. And so you have these 5 affine semigroups all pointing in different directions, and it is one of these constructions from algebraic geometry that you can glue the varieties, the affine varieties for these affine semigroups. You can glue them together to get one global toric variety, and that toric variety in some sense looks or feels like this pentagon. That's just how toric geometry works. You glue together local pieces to get one global piece, and the combinatorics of the global piece is recorded by this polyhedron. And the analogy is that you glue open balls to make manifolds. The simplest example, simplest non-trivial example, of course, there's the affine toric variety, which is just c to the n here. But if you want to glue together 2 affine semigroups, then what you do is you take the sphere P1, that's CP1, complex projective line. So what that is it's a copy of the complex numbers and another copy of the complex numbers. First copy of the complex numbers, think of it as surrounding the South Pole and just omitting only the North Pole. The second one is the whole sphere but minus the South Pole, and you glue them together along sort of the sphere, take away the North and South Pole. And the combinatorial picture is that you have an affine semigroup that points this way and an affine semigroup that points that way, and you're simply gluing together the spectra of those things. And when you glue together those affine semigroups, they sort of stop and form an interval. So the history of these were introduced in 1970, some initial theory, and then there was sort of more systematic study in the early 70s. But since then, there's a vast literature on these papers, maybe nearly 2,000, I suppose, last time I checked, under the heading of toric variety. And the prototypical result is, for instance, what does it mean for one of these things to be smooth? What it means is that the semigroup rings that you get at each of these corners is isomorphic to a polynomial ring. Now, when I say isomorphic to a polynomial ring, it doesn't have to look like a right angle as long as the semigroup itself has the right number of generators. I think possibly this one could be smooth, but this one's definitely not smooth because it has too many minimal monomials. It should only have 2 minimal monomials. This one has a generator there and a generator there, and that's it. And that's why this one looks smooth to me, but the other ones don't look smooth. Okay, present. So that was multigradings, and you'll notice that what happened with those multigradings is all the lattice. So we were looking at lattice points, and those lattice points are they're vectors with integer coordinates. So in recently in the past few years, it has become important to look at lattice points that are at points that aren't lattice points, but they have actually real exponents. So a real exponent polynomial in n variables is the same thing as a polynomial, except that now the exponent, so how do I say, this part looks the same, except that it's this Rn is the only difference here. So now I'm looking at real exponents instead of integer exponents. So these are non-negative real exponents. And the set of these is the real exponent polynomial ring. And it's got the same rule for multiplying monomials, that the product of two monomials, you just add the exponents. So for an example, you can take, why did that not work? There we go. For an example, you can take x to the square root of 3 plus y to the pi and multiply it by this more ordinary binomial here. And when you do that, you just, when you take x to the root 3 times, you say, where is it? X to the root 3 times xy squared is just x to the 1 plus root 3 times y squared. You just add the exponents in the way that you usually would, except that now the exponents are real instead of integer. And a multigraded module over this, now still monoid algebra, is the same thing as I said before. It's just a family of vector spaces. This is a vector space, but the vector spaces are now indexed by Rn instead of being indexed by Zn. So it's a continuous family of vector spaces, if you like. And then multiplication by x to the a does the same thing. If this is the vector a here, then multiplication by x to the a takes the vector space sitting at b to the vector space sitting at a plus b. So if it's b, then this up here is a plus b. The usual picture that you'd like. And that gives you a homomorphism of vector spaces from the vector space sitting here to the vector space sitting here. Okay. So real exponent polynomials behave poorly. These rings are not Noetherian at all. So if we take the ideal, the monomial ideal generated by all of the monomials that are, so no, this is not all, yeah, this is, I guess this is all the non-unit monomials, if you like. So what you can do is you can take all the powers of x1, where a1 is strictly positive. So what you're doing is you're taking generators that sit along this axis down here, and you're letting them approach the origin down there, but never actually get to the origin. And then you can take all the powers of y that go down and approach the origin like this. And what you get is all the monomials that sit in this region. It's a nice square, but with the origin pinched out. That's what this thing is. It's the square with the origin has been pinched out. This has it's countably generated because I just wrote down a countable set of generators, but there's no minimal generating set. Every time you can leave out finitely many, but you still need all infinitely many of the remaining ones. Okay, so here's another example where now there is a unique minimal generating set. You just take all the monomials that lie along this line segment, and you take the ideal that they generate. There are uncountably many monomials along this line segment, but they're all minimal generators. You can't leave any of them out. As soon as you leave one out, what you end up getting is a tiny little hole there, right? You get a tiny little hole there if you leave out, if you leave out one of the generators, and you don't want a hole. So if you want this ideal, you need all of these generators. This is uncountably generated, and it has a unique minimal monomial generating set. In contrast, the polynomial ring in x1 through xn, all the ideals are finitely generated. So this algebra becomes harder is the point. Okay, so quantum non-commutative toric geometry. Remember the picture that I had before with a bunch of semigroups glued together in ways corresponding to a polyhedron. You can do the same thing, but now instead of taking affine semigroup rings where the monomials correspond to discrete lattice points in a cone, you can take the functions to be polynomials with exponents that come from a real polyhedral cone instead of discrete lattice points. What you take is a finitely generated subgroup that's dense. So for instance, if you take the subgroup of R2 generated by 1, 0 and pi 0, then what you get is all linear combinations. So on the x-axis, you get all linear combinations of 1 and pi. And while that is a group generated, it's a free abelian group generated by two elements, in the real line, it is dense because pi is irrational. And the same thing you could take on the y-axis. You could take 0, 1, and you could take 0e, and then on the y-axis, you get a dense subgroup of the line there, and you take the product of these, you get a subgroup that's finitely generated and abelian, but it's dense inside of R2. You can take affine semigroups, so you can take semigroup rings for these kind of dense, you sort of think of them as dense subgroups of lattice points. You can glue them polyhedrally in the same way that I showed you before to get what's called a quantum non-commutative toric variety. And you can compare ordinary toric geometry, which has it's glued together from semigroups that have discrete sets of lattice points. So that's what you're intersecting with z to the n instead of intersecting with this dense subgroup G. So then the question can arise, what is a smooth such thing? We can rephrase what property that distinguishes polynomial rings from rings whose exponents are lattice points in other cases, right? So you can look at, there's a sort of, you can look at what homological properties or what commutative algebra properties distinguish a right-angled orthant from a cone that is more, so a right-angled orthant from a cone that is more sort of like this, that has, sort of weird looking generating sets instead of just a minimal generator there and a minimal generator there. So what properties distinguish that and generalizes appropriately to real exponent monoid algebras K of Q? So here let's talk about some syzygy theorems. So the Hilbert-Syzygy theorem, which I mentioned before, which is why the minimal free resolution, let's say, of monomial ideals, or really any polynomial ideals, are finite. So this says that the polynomial ring has global dimension n. And what that means is every module has a free resolution whose length is at most n. N here is, by the way, the number of variables, if you remember. This is k adjoint x, I've written here, but x is short for x1. It's short for x1 up through xn, right? So n here is the important thing. It's this n is the same as this n, which is the same as this n. That's what's going on there. So the theorem of Serre from 1956 and Auslander Buchsbaum from 1957, these are really simultaneous. A Noetherian local ring R is regular if and only if it has global dimension. So what you should think of here is that the polynomial ring is regular, and this free resolution of at most length at most n is telling you that the polynomial ring is regular. You should think of this as saying that the local ring of functions on a non-singular space is regular, and you should think of functions on tiny open sets. That's what the sort of local ring is trying to tell you. So I have a theorem. So smooth is the same thing as saying global dimension is finite. That's the really important point here. Smooth is the same thing as saying that the global dimension is finite, which is saying that all the free resolutions are finite. So I have a theorem with Nathan Geist, who was an undergraduate at the time. He's now a graduate student at Boston College. And this theorem says that the real exponent polynomial ring has global dimension that's finite. The surprising part is that it's finite, but it's not dimension n, it's dimension n plus 1. So for some reason, the free resolutions can have length 1 longer in the real exponent polynomial ring than they can in the integer exponent polynomial ring. And the same thing is true when you intersect the real exponents with a dense subgroup of Rn. So this is surprising, given that even given that this real exponent polynomial ring has finite global dimension, because it has an ideal that's generated by an uncountable set of monomials, and a priori the global dimension could be as high as n plus the index on Aleph in the cardinality of R. Now, I don't know what the index on Aleph and the cardinality of R is, and for all I know, I think it might depend on which set theory you choose or something like that. But the point is that when you look at what the global dimension could be, it could be quite large or arbitrary or something like that. But it turns out just to be n plus 1, and it's because Rn is nicer than an arbitrary ring that has an ideal minimally generated by uncountably many monomials. So this has consequences for quantum toric geometry. It characterizes smooth objects, and it has consequences for persistent homology. And I want to talk a little bit about persistent homology just to give you the connection to real exponent polynomial rings. So this is going to be a little detour on persistent homology. What's the connection to real exponent polynomials? So here the input is a topological space filtered by a set of subspaces. And that set of subspaces is partially ordered by inclusion. There we go. You just say that one subspace is smaller than another if the subspace is contained in the other. That's really all it is. And the persistent homology is you just take the homology of all these topological subspaces. If you don't know topology, don't worry about it. We're now back into the land of algebra. What we now have is a Q module, which is just a family of vector spaces parameterized by a poset. You have a homomorphism between the vector spaces whenever you have a relation in the poset. And we want it to be commutative in the sense that if you go, say, this way around from Q to Q double prime, it's Q, how do I say? Yeah. If you go from between this one to Q prime, if you put Q prime there, it's the same as going this way as if Q prime was there. So going around from Q to Q prime, it doesn't matter whether you go up through the poset this way or up through the poset that way. It's just a map from from the vector space at Q to the vector space at Q prime. So it's commutative in this sense. Let me give an example. So you can take ordinary persistence when the poset is just totally ordered 0 through m, or the real numbers. Here's what it looks like. Here's a topological space, and I'm going to filter it by taking subspaces. So here's a subspace. Here's a and its dimension. It's got 31 connected components. Here's a bigger subspace. It still has 31 connected components. Here's a bigger subspace. It still has 31 connected components. Here's a bigger subspace, but now it only has 26 connected components. Because what's happened is that, for instance, these two components, this one and this one, they joined to give me now just one component there, right? So they joined. So what's happening is that the homology at each stage is mapping to the homology at the next stage, and the number of connected components is always going down because these balls are always expanding. This has 6-dimensional, only 6 connected components. Now there are 2 connected components, and still 2 connected components, still 2 connected components, but now there's actually some loops. There's a loop that goes around this way, and if you look carefully, there's a tiny little loop that goes around that way. And the reason why this is called persistent homology is because this bigger loop persists for longer than the smaller loop. The persistent homology says that you have a map from the one-dimensional homology here to the one-dimensional homology here, but that map it takes the big loop to, well, there's still a big loop there, but the little tiny loop has now vanished and it's gone to 0. So that loop has not persisted for very long. So that big loop now persists. Oop, now it's mapped to a sum. So now the big loop mapped to the sum of that one and that one. The big loop is still there. It's just now the sum of 2 other homology classes. But one of those has very small persistence and disappears immediately. And then if I keep going, everything will disappear, right? Actually, it turns out not. A loop is created there, a very small persistence loop is created there and then disappears again. So it's a family of vector spaces parametrized by the interval there. Here's another example, ordinary 1-parameter persistence. Here is an image of Steve Marin's, of the arteries in Steve Marin's brain. This is literally my co-author, Steve Marin's a co-author. This is his brain, and you can see what it looks like 3-dimensionally. There you go. I hope that's coming out online. Yeah, and the idea is to summarize the geometry of these vessels. And so what we did was we sort of, let's sweep a plane from bottom to top and look at what's beneath that plane. So at the beginning, you have these 6 connected components. And then as you sweep up, these connected components join. There are some new ones that are formed, and then those join. And as you sweep the plane up, the whole, you're sort of, some new connected components are born, and then they join to the others. And then at the end, there's only sort of one connected component. This, so looking at how these connected components are born and then join each other gives you a summary of the geometry of these vessels in 3 space. Here's a 2-parameter version that I think actually conveys to a commutative algebraist much better what is going on. So here are some normal flywings. Are there any conditions or restrictions for the dimensions of the vector spaces? So you'd like, so in the theory of this stuff, what you do is you'll define, I'll actually get into this, there's a notion of tame, and what you want is that the vector spaces all have finite dimension, and somehow you want to impose that there are only finitely many different ones. So I'm going to get to that very shortly. That's a great question, Jonathan. Yeah. So let's do the flywings, and then I'll be able to show you what the conditions on the vector spaces look like, actually.
Ezra, we lost Ezra.
Yeah, okay, it turned on. Good. Okay, it came back easily. Good. Sorry, I know that my camera just turned off. If it does that again, just tell me, and hopefully we can avoid it doing that. I don't know why it turns off every now and then. It's maybe it's just an old camera. But everything's back. Yeah, everything's working again?
Yes, yes, it's working.
Okay, so these are normal flywings, and so all their topology looks the same. So the topology of this wing looks like the topology, looks like the topology. They're all the same, kind of. These are topologically abnormal, and I'm just going to show you what the differences are. In talks in person, I like to, raise your hand if you see what the difference is, but try to find the differences before I show you. This one has an extra little triangle up there. This one's got a wiggle. This one has an extra bar right there, an extra cross vein. This has an extra triangle. This one has a missing intersection point, and this one has an extra cross vein that sits over there. So these are topologically abnormal wings. Here's a photographic image. It's a close-up of the one with an extra bar, but you'll notice actually the extra bar doesn't quite meet over there. Isn't that interesting? In any case, Here's a spline that the biologists draw from this, and you'll notice that actually the extra crossvein isn't drawn there because they sort of only know about normal flywings. The whole point of this study is to study the abnormal ones when the planar graph changes. The hypothesis is that topological novelty arises. Well, I don't want to explain exactly what this means. Essentially, what it means is if you have selection and you push the selection too far, then what happens is the selection is giving you sort of all these gradients of proteins and so on. When you push it too far, it goes beyond some threshold and a new vein appears. This is a biological hypothesis we'd like to test. And to proceed, what you do is statistics with flywings as data objects. That's actually what the biologist would like. But what you do is you summarize the flywing as a multi-persistence module and use those as data objects, and then do statistics with multi-persistence modules. So let me show you, this is universally applicable with the fact that it's flywings. It's kind of neither here nor there. Let me draw you and show you what's going on here. So you encode the fruit flywing with 2-parameter persistence. The first parameter is distance from the vertex set. So these are points in R2, and you expand them just like we did before, right? You expand these points like this. And then the second parameter is distance from the edge set. These are given as Bezier curves, and they are actually given as Bezier curves. And now you can expand them like this, right? So you expand the edges like this. So then what you do is you take, you require distance at most greater than or equal to minus R. Distance less than. What does this mean? What it means, you take a subset that is near the edges but far from the vertices. So the subset of the set that you're taking the homology of is this. You remove the blue points, the blue disks from the red stuff, and then you get this topological space, and you take its homology. When R and S go up, the topological space gets bigger. So what you get is a family of vector spaces indexed by the choices of radius and semi-thickness, R and S, radius and semi-thickness. And when R goes up, so when the disk gets bigger, when R gets bigger, the disks are getting smaller, and so the topological space is getting bigger because you're removing smaller disks. That's why there's a minus R there. You're removing smaller disks, which gives you a bigger topological space, and that makes the maps go in the correct direction here. That's all that means. Let me draw let me show you a toy example of this. So just to summarize, the discrete case where you have the exponents coming from z to the n, that's usual combinatorial commutative algebra. And when you have the exponents from Rn, that gives you this sort of more modern view, and that's real exponent polynomials. And that's there's a paper by Lesnick on this in multi-parameter persistence land, and then a lot of theory that's been developed since then. So let me show you what this looks like in a toy example. So here's a piece of flywing vein. And what I'm going to do is I'm going to expand. So I'm going to move that. So here, what's happening? Here's the multi-persistence module, and I'll show you in detail what this looks like. But if I move this guy, it changes what the module looks like. So here, for instance, if I take the radius to be big, so this is big R, right? So this is R over here. So this is R is big in absolute value. Think of it as a big blue disk. Then there are these 3 connected components. There's one here, and one here. So this is 3-dimensional vector space, Jonathan. So this is what you should be looking at. And then when the radius and the edge thickness are approximately equal, that's in this region over here, then the vector space dimension is 2, because there's one connected component there and one connected component there. And when the semi-thickness is big compared to the radius, then the red stuff has just one connected component, and that's that one that's going on over here. So what's interesting about this is it's an R2 module. Here it changes depending on, okay, so it's R2 module. It's acted on by real exponent polynomials in the sense that when you make the radius, well, when you make R and S get bigger, then you have maps on vector spaces that go like this. And you should think of this as being, well, there's 3-dimensional vector spaces there, 2-dimensional vector spaces there, and 1-dimensional vector spaces there, and there's only finitely many regions. That's the tameness criterion that you want. So it's not Noetherian, but there's some finiteness type condition that you can put on these things, and that's the key point here. You can discretize and make it look like this, but why? Because the more you discretize, the harder it is to write down these modules. You should instead just write down equations for this curve and for that curve. It turns out these are just quadratic curves. Well, that curve, and actually there's that little bit down there. Okay. All right, so module theory, there's some prior research on these modules, but not very much. The good news is that multigraded analogs exist for Noetherian. That's the tameness condition I just talked about for minimality and primary decomposition. Bad news is that you have to give up on looking at free resolutions. Well, at least for finite free, you can't ask for finite free resolutions because the ranks have to be uncountable. There's just nothing you can do about it. And the good news is the syzygy theorem still works. And the interesting part is that the proof of that syzygy theorem used methods that were developed for Kaplansky's problem. So let me just briefly tell you what happened with Kaplansky's problem. And these are canonical minimal monomial resolutions. And this is with Jack Egan before he unfortunately died a couple of years ago, and a former graduate student of mine, Erica Ordog. And so for characteristic k is 0 or sufficiently large prime, Kaplansky's problem is solved with the entire wish list. So it's universal, canonical, closed form, combinatorial, minimal free resolutions. And so we've given maps on homology, homomorphisms on homology from I to I minus 1. And each is explicitly given by a matrix with combinatorial entries. And I can write this thing down and you can see that it's an explicit sum over some explicit set here of some explicit numbers with some explicit weights. And lambda AB, so the sum is overall saturated lattice paths. Those are sums over lattice paths which combinatorialists like. There are these chain link fences, which are combinatorial gadgets that we had to define in terms of simplicial complexes, the Cazul simplicial complexes sitting at the various lattice points. There are weights, and then there are these denominators over here, which come from sums of square products of sums of determinants of submatrices of the boundary differentials. These are sort of matroidal information. That's what this stuff is. So you use more Penrose pseudo-inverses. This is how we can manage not to make choices. The choices are sort of quote-unquote canonical when you can choose these splittings of maps, and the resulting split spectral sequence is a minimal free resolution. So that's a very, very brief summary of something that should take an entire hour to describe. But the point is that the problem is solved, and the methods that were used to solve this problem were then used to prove the syzygy theorem for real exponent polynomials. Even though this situation here is completely discrete grading monomial ideals in the classical combinatorial commutative algebra setting, but the methods you apply to the real exponent polynomials. Okay, just a glimpse into the future briefly. Looking forward, we can be looking for invariants or features of R to the n or Z to the n graded modules. These are important for data analysis based on persistent homology. Since persistent homology gives us Rn graded modules, we should want to do commutative algebra with them. And everything that we like to do, we'd like to then do statistics on it. So these are valued in metric spaces. So we want to say how far apart two modules are. And we want to say, you know, what is expected from a random Rn graded module, right? Because if you're doing statistics, you want to know, are these modules random, or is there some bias, and that bias therefore telling you information about your data set? So these are great questions just about commutative algebra. There's been sort of a turn in classical commutative algebra toward asking questions, what does a random object of this sort look like? And we need to do that more, and also for Rn graded modules. For minimal multigraded resolutions, you can ask for real exponent Cazul simplicial complexes and analogs of Hochster's formula, but we don't know what the minimal free resolutions of these things look like. You can look for combinatorial representations of Hilbert series, although they're not going to be series in the usual sense because they're going to be sums over, sort of Rn instead of over Zn. But you can ask, what should you do with local cohomology? I mean, there's no Noetherian condition here, so local cohomology is not so well behaved. But is there something we should be using instead? Some sort of real exponent analog? And for quantum non-commutative toric varieties, is there, what does sheaf theory look like? Is there a notion of Cox ring and this kind of nice combinatorial commutative algebra and its interaction with algebraic geometry? These things are all kind of wide open at this point for investigation. And with that, I'm going to leave you with some references here, and there's some references here. And if you want these slides, just write to me, no problem, I'll send them to you, and it has all these references. And thank you for your attention.
Thank you, Ezra. Are there any questions, either from here in Zoom or in YouTube? You have a question, you can say it aloud.
Or you can write in the chat. I'm looking at the chat too.
I have a question.
Yeah.
Thanks, Ezra, for your talk. I loved your pictures. My question is how we can compute the minimal generators for the, I mean, with we consider a standard grading, we usually using Grobner basis, but
Mhm.
in this case, where the exponents are real numbers.
Oh, yeah. That's an excellent question. How do you compute these things? So let me get back to a slide where I have pictures of these. So in this particular, so in a case that looks like this, so what does it mean to compute the minimal generator? So one of these papers, now let me go to the end again. Actually, it's in, where is it? Integrated algebra, this one. So in this paper, there's a data structure introduced called a monomial matrix. So how do you write down maps in minimal free resolutions of, let's say, monomial ideals? Well, because everything's n to the n graded, what you do is you write down, let me get to the other slide, let me get to the one with the actual picture here so I can draw something on it. Okay, so so what you do is you write down a matrix, right, with scalar entries, so lambda ij like this. And what you do is you label the rows and columns with vectors a1 up through ar, and then b1 up through bs. And then what you say is that the free module generated in degree bj maps to the free module generated by degree ai with a scalar lambda ij. Now, what's important there is that the free module generated in degree b here, this is, say, bj, and the free module generated in degree ai, what's important is that bj be bigger than ai, so that you can say what it means. So this generator here gets mapped to lambda times the sort of the monomial that occurs in this degree. So this free module down here, this free module, has a monomial in degree b. And this generator of the b free module maps to a scalar multiple of the monomial that sits in the a free module. And the lambda just tells you which scalar that is. Here's the thing. There's no reason why this thing has to be an orthant and why this has to be an orthant. You could have instead, let me choose a different color here. You could have instead made this a thing into a, now let me do it. Let me take a light blue color here. So you could have had just any upset sitting over here, and you could have had any other upset sitting up here. And you can ask, what's the coefficient for the inclusion of this upset into this upset? And that's what gives you modules that look like this. So what you end up doing is writing down the whole orthant for this, and then you say, oh, well, then there's this thing, and then there's sort of this thing. And you just sort of take those big chunks and you map them between each other. But there's only finitely many chunks, and so there's only a finite matrix that you have to draw over here. Does that make sense? Kind of, sort of, right? The point is that there's only finitely many of these regions, and because there's only finitely many of these regions, there's only finitely much information to write down in terms of how to map the various modules to themselves, right? So instead of thinking of this region as having lots and lots and lots and lots of minimal generators that sit along, sort of uncountably many minimal generators that sit along this curve, just think of it as they're all the points that sit above that curve, and just write down the equation for that curve, and that's the data structure that you have, is the equation for that curve instead.
Okay. Thank you so much.
Are there any applications of Sylvan ideals in biology? Not as far as I know. So the study of the Sylvan ideals, that was purely, people wanted to know for 60 years what's the minimal free resolution of a monomial ideal supposed to look like, and
Oops, we lost Ezra again. He comes back soon as before.
And
Yeah.
I'm back. Good.
Yes.
So what happened was that, so there's a connection between the Sylvan ideals and computational topology, interestingly, and so applied topology, is that I sent Erica to a talk that was explicitly about applied topology, and it was about sort of matroids and these splittings and that sort of thing. And I sent her to this talk because Erica had figured out more or less how to do minimal resolutions of monomial ideals in 3 variables, and it had to do with planar graphs, and you do all sorts of things, but planar graphs are just examples of matroids. And so I sent her to this talk that was basically about sort of matroids in higher dimension. And I sent her to this talk about matroids and computational topology, thinking that there might be a connection. And so she went to this talk, and then she came to my office after the talk. I couldn't go to it myself, I was teaching at the time. But she came to me after the talk and she said, I know how to do the n-dimensional case. And so it was computational topology that gave us the answer for the Sylvan resolutions. But the Sylvan resolutions themselves were really just a pure math problem that had nothing to do with biology. There are, of course, connections between monomial ideals and sort of all sorts of science and statistics and these kinds of things. There's connections just because they're very basic objects of just partially ordered sets of integer vectors, and partially ordered sets of integer vectors come up anywhere. But when you look at Sylvan ideals, so Sylvan ideals are just really, it's really Sylvan resolutions. The ideals are just monomial ideals. It's the Sylvan resolutions. And looking at the combinatoric that comes up in the Sylvan resolutions, it's sort of one of those things that it's nice that it's there, but at the moment I don't see how to use it for anything except that it kind of tells you how to fill in the minimal free resolution before you start, and it might be really efficient. So actually Sylvan methods might give us the most efficient way to compute minimal free resolution of monomial ideals. But it's not directed specifically at biology. It's just a pure math and computational math thing that is sort of universally applicable because it's math. Progress on the Hilbert series question. As far as I know, no one's thought about it. No one has thought about Hilbert series. Well, okay. People doing multi-parameter persistence think about Hilbert series all the time because it's called the rank function. So it's the rank of the module. It's not the rank function, it's really the rank of the module. So people in multi-parameter persistence think about Hilbert series all the time, but they don't, other than writing down what I just wrote down here with these sort of finitely many regions and writing down the vector space dimensions on those regions. I don't think people have a framework for doing Hilbert series in this Rn continuous multigraded land. I think that theory just has yet to be developed. And so there's theories about how to write down resolutions and stuff, but the finiteness properties of those resolutions, see, ideally you'd like to take sort of alternating sums of simple looking things and get expressions for the Hilbert series of the more complicated things. I think that in principle could be doable, but I don't think that theory has really been written down quite properly yet. There's sort of a lot of dancing around it in the literature on persistent homology, but no one sort of squarely said, let's write down a theory of how to write down Hilbert series in real multigraded land. Luis, you're muted if you're trying to speak.
Sorry. Yeah, I have a few questions. In these pictures, you mentioned that the borders were quadratic. So in general, the borders are polynomial curves or polynomial objects?
Excellent question. So this boundary over here. So let me get to another copy of this picture that's not so adorned. Okay, good. Here's another copy of the picture that doesn't have so much drawn on it already. So you're asking about this boundary region over here, this boundary there, and this boundary curve there, and that, and this, right? Yeah. You're asking, why should I even expect to be able to write down an equation for that, right? That is, why is it semi-algebraic? The reason why it's semi-algebraic is because the calculations that you do in multi-persistence are often kind of semi-algebraic. What you're asking about in this, let me describe it, why it's semi-algebraic in this case, and that will tell you sort of why you sort of generally expect it to be. The reason why it's semi-algebraic in this case is because you're asking, when is the distance to this point less than or equal to the distance to this line? And now if you think about how the Greeks thought about a hyperbola, that's a hyperbola, right? When the distance is equal, that's a hyperbola. So it's a quadratic. So the point is, it's always looking at distances between things that you can write down. Things that you can write down tend to be finite. And when you start writing distances between them, they're algebraic equations because they're just, sums of squares, square root, but you can remove the square roots because you just want things to be equal. So you end up with algebraic equations that way. So it is semi-algebraic. It's not a theorem that everything's semi-algebraic. It's just, if you were giving these things to a computer to begin with, to compute with, then more likely than not, things were semi-algebraic in a natural sense.
Okay. And then last question, because you mentioned in future work like something like local cohomology, and the first thing that popped up in my head was D models. Like there is any hope that one can have like a differential operator for this kind of semigroup?
Right. So one should be able to look at D modules in this setting. I mean, this is just a semigroup ring. You can still take derivatives, and you can ask now about the action of differentiation and multiplication together, and you should still get some. There should still be a notion of D module. I have no idea what kind of behavior you get. I don't know what the analog of holonomic would be. There still should be lots of things to say, but I don't know what the baseline of objects to look at that should behave well. I don't know what that baseline should be. So when you look at the modules themselves, the multigraded modules themselves, this notion of tameness, where there's finitely many regions, each of which has a finite dimensional vector space associated to it, that's great. I do not know how that interacts with D module land, but maybe it interacts nicely. And maybe the fact that the ring has finite global dimension might make the algebra. Why am I not remembering the name of the algebra? D. It might make D behave well. What's that algebra called again? It's escaping me.
This will be like I know. I mean,
Weyl algebra. It's called the Weyl algebra. That's right. We might make the Weyl algebra behave well. In any case, yeah. So, as far as I know, completely unexplored, but could be interesting. And frankly, if it gave you finite ways to represent these things, that'd be great.
Yeah.
I don't know how that would happen, but maybe in the semi-algebraic case, maybe there's some way that it interacts with the D module constructions. That'd be really cool, actually, if that was the case.
Well, thanks, Ezra, and we thank you again for the great talk. And I think it's time to stop so we don't take time from the next talk.
Right. Thank you, everybody. Bye-bye.
Bye. Thank you. We're on time. I want to say thank you, Luis and Ezra, for participating in this conference. Thank you for your support. Ezra, thanks for accepting the invitation.
It's my pleasure.
We are on time for the next talk. Let me see, Nelly is here.
Okay. Well, thanks for the invitation. So my name is Nelly Villamizar. I am an associate professor in Swansea University in the UK. And I'm going to talk about my one of the areas of my research. So I'm going to explain all the words that you see there, in particular spline. So this is going to be a general talk. If you have questions, please let me know. My main idea is I want to explain what are the connections between splines and some of the tools or some algebraic things that you might know. So, one second. So a spline is a piecewise polynomial functions, which is defined on a partition of a real domain. So for example, if you have a triangulation, as we have here on the left, so you can think of, so a spline is a polynomial when you restrict to each triangle, and what we would like to have is a function, which is a piecewise polynomial function. So we will be thinking of a smoothness across the common faces of those triangles. If we are in 3D, for instance, we can have a tetrahedral partition, or we can have some other partition with some other kind of polyhedra, or we can go to higher dimensions. So the idea is you have a partitioned domain, and you want to construct piecewise polynomial functions which are smooth and to certain order on the whole domain. So, so if we have an integer, a positive one, we can fix what is the order of smoothness that we want. And we want to find, so every time we fix the partition, we want to find functions which are defined on that partition so that the restriction to the maximal faces of that function is a polynomial in n variables, depending on the dimension of your polyhedral complex. And we want that the function is CR continuous on the entire domain. That means that we want the functions to be continuous, so to be a function on the partition, and we want the first derivative, second derivative, and up to derivative R to be continuous. So this space is a ring. So you could think of having two functions, which are piecewise polynomial functions, which are CR on a given domain, and you can do a piecewise multiplication, and you are going to have a function which is again CR continuous. But if we fix the degree, so that means we are not able to multiply, we are not necessarily able to multiply two piecewise polynomial functions there. But if we think of this when we fix a polynomial degree, then we could multiply by constants. So we will have a vector space, and that means, well, the degree of every polynomial, so the degree of actually each polynomial on each of these pieces of the partition is going to be a polynomial of degree bigger or smaller or equal than d for each of the maximal faces. So this is a vector space over R. And this space is quite important in applications when you want to have shapes, say in the computer, if you want to have a curve, if you want to design the letters that we see in the computer. Actually, what is using is piecewise polynomial functions. In that case, for the curves, it will be defined on an interval, or actually several intervals glued together, and then you have some curves on it. Or you can have in 2D, and then you have surface models of cars, of airplanes, or tools. Some of those things, some of these functions are used for those kind of applications, and particularly it is important to have a small polynomial degree so that you can have more control on what is happening with the shapes in an easy way, and an intuitive connection between the degree, the number of control points, etc. So in any case, this is a vector space for us. We will not talk about the applications, but we would like to see this as an algebraic object. So if we have say if we have two tetrahedra, say, suppose we are in 3D, we have two tetrahedra, and if they join, or if they have a common triangle between them, then this is going to be a two-dimensional face, right? And we will say that two polynomials, so one on supported on each of these tetrahedra, So the difference between those polynomials should be an element in the ideal generated by the power of the linear form, defining this the hyperplane which contains this common phase, right? This is just a generalization of what we call the factor theorem in 1D. And it happens also in higher dimensions. So that means that every time that we ask for a piecewise polynomial function to be CR continuous, we will like that the neighboring polynomials, the difference between them, is going to live in an idea, correct? And which idea? Well, here it becomes very relevant. The power of, so the ideas generated by powers of linear forms, correct? So this is the characterization of the space of the splines algebraically speaking. So this is how splines look like, just to, so if you got lost already. So this is just an example of a spline. If we have a partition in 2D, then you can have a linear spline. So this will be linear polynomials on each of the faces. And what we would like to describe or to have is this kind of surface on it. Or we can go to higher dimension, a higher degree. So this is degree 3 polynomial, and also the first derivative is continuous across this common phase. So these are the polynomial, these are the splines. And what I'm asking is, for example, what is the number of linearly independent functions which you can have as piecewise polynomial functions of degree 3 such that the first derivative is continuous. So for example, but we work for degree D and smoothness R. So this question about what is the dimension of this vector space has been open and is still open for in general. And so these are just some results or what is known nowadays for the two-dimensional case. So the first person who talked about this problem in general, as I said, this problem on computing the dimension of a spline space for a given R and a given D was Strang in 1974. And he proposed a conjecture, more or less, it was a combinatorial formula, very similar to the one you see here on the screen, except that the last term was not really there. But Strang had the intuition that this first part was not really giving him the dimension of a general spline space or a general triangulation, but he put the conjecture, and some other people put this other term here, first for particular cases, and then Shoemaker, he's working in approximation theory, so no algebra at all. Well, not at all, but not algebrist. So he proposed this combinatorial formula, very similar to the Strang conjecture, but with this term. And he proved that this gives a lower bound on the dimension of the spline space when you take triangulations. So this formula, it takes into account the degree of the polynomials, the minimum order of smoothness that you want. This is the number of one-dimensional faces, so that means of edges. This is the number of interior vertices of the partition. And here there is a term which counts the number of different slopes that you have at each vertex. So the slopes are counted according to the number of edges that you have there. If they lie on the same line, then you just count one. So you are counting different slopes of the edges at each vertex. So this formula is known to be in a lower bound. And then since then, everybody has been trying to prove that this formula actually gives the exact dimension for the spline space. This is easy to prove. So the question is that formula the dimension of the spline space for triangulation? So Hong was a master student with Peter Alfred and Shoemaker doing approximation theory. So when the difference between the degree and the order of smoothness is large enough, so they are not so close to each other, then this formula gives the exact dimension of the space. So when D is bigger or equal than 3R plus 2, then this formula gives the dimension of the space. there was a conjecture. Now they are from applied algebraic geometry, Hal Schenk and Peter Stiller. They put this conjecture saying that this formula was given the dimension of the spline space if D was bigger or equal than 2R plus 1. However, so this example here, this triangulation gives an example of a triangulation for which this formula doesn't give the exact dimension when D is equal to 2R. And the one here actually gives a counterexample for the conjecture, which says that actually this dimension here is higher than when you compute this term. And so this conjecture is not true in general. It's still open to see if actually for generic is actually gives the dimension. And well, they were trying to see, and then if it's not 2R, then which is the number? So they proposed to be 22R plus 7/10. Well, this, just to say that all this work comes from algebraic geometry and commutative algebra. So the work about what is this irregularity. Okay, so I'm going to talk particularly of the three-dimensional case. So the question is the same. What is the dimension of the spline space when you have a tetrahedral partition? We restrict to tetrahedra because it's easier. Also before, you restrict to triangles is because it's easy to explain, but you can also have squares or rectangles, anything like that. But obviously the formula has changed a little. And here we restrict ourselves to tetrahedra just also to make the talk easier. So here the results are a little less promising than before. So here we know what the dimension is of the space if we only ask for continuity. So if the function is actually a function, if it's continuous on the whole domain, then we know what the dimension is. And this was proved by people in approximation theory, Peter Alfred, Larry Shoemaker, and Marixa Sirven. It was also proved by Vilera, so he was using homological algebra and some of the tools that also the people in the previous slide were using. But so this is the result that is for sure there. For higher smoothness, we have lower bounds and upper bounds. So, and we have the dimension when the tetrahedral partition is generic. So if the degree is bigger than 8, then the dimension, we know what the dimension is for generic tetrahedral partitions. This is a collaboration of people in approximation theory and rigidity theory, which makes things already a little more interesting. Now, there are bounds that has been computed for any R and any D, and here there is work combining approximation theory and also some work doing homological algebra and, well, commutative algebra. So in particular, I'm going to talk about these two bounds. So one is for tetrahedral vertex stars. So that means that we have one vertex and we have tetrahedra around. The vertex could be on the boundary, and then we have that every tetrahedra in the partition has that as a vertex, or we can have a vertex around it, so an interior vertex. Those will be a start of vertices, and then we will use those results in those particular partitions in order to prove a lower bound on a more general partition. So when we have several interior vertices and also several exterior ones. The bounds here, as you will see, they use several tools for commutative algebra, and those are the best bounds known nowadays. So I will try to explain what are the tools that we use to prove that. So first of all, this is just the explanation that I said. We first will consider tetrahedral vertex stars. So that means that we have tetrahedra and they all have a common vertex that we can think of this as being the origin in R3, okay? As this is some notation that I use all the time. I hope you already saw. So we have faces of dimension I So we have a dimension 3 here, so that will be the tetrahedra. We have all the triangles, will be delta 2. We have all the edges, delta 1, and the vertices, which are delta 0. And when there is a little thing on top, it means that the face is an interior one. Every time that I have this L, this denotes the linear form which is vanishing along or on the hyperplanes, and in this case, on the planes or on the triangles, which are part of the partition. So these are these L's, and every time that I see them, I will tell. But these are essentially what we are going to use. Obviously, what we want to find is to find a formula for the dimension, which is meaningful in terms of how many faces, so how many tetrahedra, how many triangles, etc. Something that we can read of and combinatorially, right? So this is the goal, to have such a formula. So we fix the R and D. So, and this is the spline space that we take. So we want to have all the piecewise polynomial functions. We want polynomials on each of the tetrahedra. And in particular, when we consider a star of vertices, so every tetrahedra is going to have the same, sharing a vertex with the other, so we can put that in the origin. So in fact, we can consider all these hyperplanes, so all this going through the origin. And we can, in fact, consider the homogeneous splines. That is because we can go degree by degree instead of considering, so these are all the polynomials of degree less or equal than d, but in the homogeneous case, so if we put this common phase at the origin, then we can count, if we want to count the dimension of this space, we can count going degree by degree by counting the number of independent homogeneous splines on the partition. So this is what it says essentially here. So there were two formulas that were proved by the people in approximation theory back in 96. And those formulas were for homogeneous splines. So these formulas are slightly different when you have a vertex which is on the boundary and a vertex which is interior. So there is, this is the notation that we use. This is for the open vertex star. So the formula is, there was a combinatorial formula proved and is for open vertex star. So the vertex is on the boundary, and this other one, which is for vertices in the interior. So the formula for the open, for the dimension of the homogeneous spline on open vertex stars actually gives the dimension, the exact dimension, if the degree is bigger or equal than 3r plus 2. However, if we are talking about closed vertex stars, then this formula gives the exact dimension if the degree is bigger or equal than 3r plus 2. But if it is, if this is smaller, we don't know if this formula gives a lower bound or not. So I forgot to say that in the other case is always a lower bound. But in this case, if you have an interior vertex, then we don't know if actually, if you just happen to have a D which is smaller than 3r plus 2, we don't know if this formula is giving you a lower bound or not. This might not be really a big deal if we just have a vertex star, but we need to think that we want to use these formulas in order to compute or to say something relevant when we have a partition with many of them. So, and there are other things that will happen, and it will be, we really need to know what happens if D is smaller than 3r plus 2. We cannot just put a formula there which might not be a lower bound. So what we, so this is just an example. If we take, for example, polynomials of degree D and we ask for smoothness 4, then the dimension, so that means the number of homogeneous splines on this partition is 21, but the number that is that you compute from this formula is 27, which is not a lower bound. So what we proved with Michael Di Pasquale, who recently moved to New Mexico, then what we proved there, what we proved with him was that this formula is a lower bound if D is bigger or equal than 3R plus 2 over 2. Let's notice that the difference is not really much. Well, it's 3R plus 2, what we know, but now we improve it to 3R plus 2 over 2. But this is interesting, but what is more interesting is that if we look also what people in rigidity were doing, we can generalize a result that it was used for the two-dimensional partition. It can be generalized to 3D. And actually what happens in the smallest degree is that you cannot find anything which is interesting in that space. Meaning that if D is too close to R, so if D is smaller than 3R plus 2 over 2, then the polynomials or the piecewise polynomial functions, they must be polynomial, meaning there is only, the polynomial should be the same polynomial on each of the tetrahedra, that you cannot put two polynomials differently and still have the same order of smoothness. And that's great. So that's not happen. That doesn't happen for 3R plus 2, but it does happen for 3R plus 2 over 2. Meaning, we know what is going on with this formula always. So this formula is going to help us giving a lower bound. But if we don't have a lower bound, we actually don't worry too much because actually we know what is the number of splines. Actually, it is just the dimension of the polynomial space in that particular degree. Right. So, and what is this result uses is several things. So first of all, so these are the three things that we use. First of all, I'm going to show you just briefly how we compute this dimension, where these formulas, this LB appear, and so I'm going to show you what we call the Villera, Schenck, and Stillman chain complex. So we are going to use the polyhedral complex extraction of the domain. And we will use that to construct a chain complex. And then we will have the dimension of modules and the dimension of the homologies. And then we will have a formula for the space. We will see that in a second. Then we will use a polarity. So a polarity comes from the relation between the splines and the dimension of the ideals generated by the powers of linear forms, which are vanishing on these hyperplanes, which are part of the partition. So here is this a polarity, just to, this refers to a way of computing, or the relation between ideals of fat points, which will be in projective space, and the dimension of ideals generated by powers of linear forms. And since we are particularly interested in partitions in 3D, that means that when we take the dual, so when we take the line and instead of taking the line, we take the three coefficients and then we consider that as a point in P2, then we are particularly interested in fat points in P2. And we are going to use an inductive procedure that determines the dimension of that fat point's ideals. And this was done by Cooper, Harburne, and Taiter in 2011. Okay, so let me show you those tools very fast. So this is going to be in 3D again, so as we have been doing. So we have a tetrahedral partition, this delta in R3. We consider it as embed in R3, right? So you don't need that, but we actually need it. This is going to be embedded in R3. Since it looks very convenient that we can consider just splines of or homogeneous splines, so we want to count the dimension, but it will be nice just to go degree by degree. We are going to homogenize the problem. That means we are going to construct a cone as we see here. So instead of having this triangulation, we have the tetrahedral one, and we construct the cone in 4D. And instead of having, or instead of taking the ring in 3 variables, we take now 4 variables, but we have an advantage now, and it's that we will have a homogeneous polynomials, right? And then we want to take ideals, and we somehow I said that for each hyperplane, so in this case, for each plane, if you take tetrahedra, so each of the triangles of the plane, they are going to vanish, and we can take that this linear form, which is vanishing along those faces, and that will be the linear form L sigma. Sigma is for each triangle. But now suppose you have an edge, and the edge is contained in several of those triangles of which are faces of the tetrahedron. So when you have an edge, you take the ideal which is generated by the power of the linear forms which are vanishing on all those triangles which have this edge as a common face. And similarly, as you have a vertex, then now you are going to take all the triangles which contains that vertex, and the triangle must be part of the partition, obviously. And you take the ideal which is generated by the power of the linear forms of all those vanishing of all those on all those triangles, and that is going to give you an ideal which is associated to the vertex. A long story short, we can construct this chain complex. So we will have, we take the ring as the rings in 4 variables, and we will have a term which is associated to the tetrahedra, and then we use the boundary map, which is from this simplicial complex, and we can go to this term which is associated to the triangles, and similarly, we go from the triangles to the edges and from the edges to the vertices. So these are the boundary maps. We are taking coefficients from the ring in 4 variables, for the polynomial ring in 4 variables, and we are taking the quotient. We are considering all these ideals that I defined. So one will be for the vertices, one for the edges, and one for the triangles. And we just take 0 as the ideal for the tetrahedron. Then you can think of having this other chain complex associated to just the ideals, but then we can take the quotient and we have tests. What happens with this is that the spline space is isomorphic to what is to the kernel of this map, to the first top homology module. Because, well, when you just think of what is the boundary map doing, when we map the piecewise polynomials to this quotient, then what it says is that every time you have 2 polynomials which are supported on 2 neighboring tetrahedra, then we want the difference to live in the ideal. We look for elements in the kernel. So that means we will look for this pair of polynomials supported in them in neighboring tetrahedra, such that the difference is going to live in the ideal, which is generated by the power of the linear form. So you take the kernel of this map, you are going to have the space of splines that I would like to find. That means that if I compute the dimension of that kernel, then I will have the dimension I was looking for. Then, since this is a simplicial, a chain complex, we can write the Euler characteristic equation, and we can have a formula for the dimension of the kernel of this map of the top homology module in terms of the dimension of the modules which appear here, and also the homology terms, or the homology, the other homology modules which appear when you take the Euler characteristic equation. Correct? So in principle, I will put all the homologies on one side, and then all the dimensions of the alternative sum on the other side. But since we are looking for this, then all the others go to the other side. So we would like to compute each of those terms if we were going to compute the dimension of the spline space by using this technique. So There are several terms in that. Let me just put everything so maybe you can read. There are several terms in that formula or in that expression that is easy, they are easy to compute. For example, we go one by one. So this one is the dimension of the polynomial ring in 4 variables of degree D. That's just the E plus 3 choose 3 because we have 4 variables and this is just polynomials of degree D. So that's it. We go to the next. So here is quotient. Well, actually I removed the quotients. I simplified a little from the formula before to this, but okay. We have a quotient of the polynomial ring over this ideal. So essentially we would like to compute the dimension of this ideal, which is associated now to, sorry, it should be a 2 here, to the triangles. This is edges and the other is vertices. So to the triangles. This is just, this is an idea generated just by 1 power of a linear form. So we can compute the dimension easily. The power is r plus 1. This is only just 1 linear form to the power r plus 1. So the dimension of that ideal is this. Is the d plus 2 minus r choose 3. Now, if we go to the edges, so now we have an ideal which is generated by powers of linear forms. But they have something in common, and is that all those planes, which are vanishing on those linear forms, all those planes have a common edge. So I can reduce the number of variables, and I somehow, well, I return to some of the cases which were already considered in the 2-dimensional partition. So this is the dimension of this ideal. We can easily compute it, and it's also a combinatorial formula that is given here, correct? If we go to the vertices, then we have a bunch of linear forms which are vanishing on 1 point. So we are in 4 variables. If we can reduce 1 variable because they have a common vertex. So that will be an ideal generated by powers of linear forms in 3 variables, and we do not have a formula for that dimension. So that is our first problem. We can see what happens with that particular dimension, but in general, this is something that we don't know, or we don't have a resolution for such ideals. I got something in the chat. I don't know if, nothing. Okay, fine. So, correct. So those are all the things that we need to compute. And so I think I have probably 10 minutes, 12 minutes. So, okay, so, but okay, you got the idea of all these problems. So, sorry, I didn't say what the other problem was. So here, we don't have this, we don't have a resolution for this kind of idea. So what we are going to use is what we know about the star of vertices, of splines over the star of vertices in this particular point. If this were a general tetrahedral partition or a generic tetrahedral complex, then we will need to compute these 2 homology terms. What happens in the 2-dimensional case is that there is only 1 homology, and so we can easily assume that that is 0 and then give a lower bound. In this case, that's not what happens because they have different signs, so it's not enough if we just say that, okay, let's say that they are 0, right? So this is not what we can do, and this is also what makes very difficult to compute lower or upper bounds for the dimension of the spline space over tetrahedral partition. And also you can somehow extrapolate this to higher dimensions when you will have more homology terms, and then you will need to compute more, and there we have different signs. Well, okay, but we are in 3D. So when we consider just these ideas, like or when you consider the case when we have a common vertex and all these tetrahedral around, which is helpful for us in this particular term when we have a larger partition. So we have several results on the homology of those, on the spline space. These are the homogeneous now because we moved that vertex to the origin and we talk about homogeneous splines. So there is one trend which is going to vanish. Also, well, if D is big enough, and then the homology is going to vanish. So this is the dimension of the spline space when this homology appears here, and when D is big enough, then we know that the dimension of the spline space is actually the same as, well, that the ideal actually generates the entire polynomial ring. And in that case, the dimension of the homology is equal to 0. So this is the formula that we get for the lower bound for the closed vertexes, for splines on closed vertex stars. This formula comes from this complex, which is the complex that I explained to you before, but it's the complex when you just take one common vertex between the tetrahedron. And we have that the dimension is this formula gives the dimension, this lower bound on the dimension of the space whenever we have that the ideal actually generates entire polynomial space, because in that case that homology is 0. In order to prove what I said, so this is the explanation of the first the first tool that we use to compute the dimension of the spline space is to put everything encoded in this in this chain complex. Now, when we want to compute or to have results such as when or what is a value for which we can say that this ideal J is equal to actually the whole polynomial space, then we use some of the, so we dualize the problem, and we use some of the results which are known for the dual part, which is called the ideal of powers, the ideal of fat points. Why do we do that? Well, because many people work in ideals of fat points for many other reasons, not for splines. And there are several results, not particular, there are results for P2, as we will see in a second, but there are results for Pn or P3 or like some conjectures also. So it's very interesting to connect or to see the dual pictures of these and see what is going on there. So particularly how it looks like if we have a octahedron, and this octahedron is so we have tetrahedra, right? We have 12 tetrahedra. Is it correct? No. We have 12 planes, 12 triangles in this partition when we have 4 tetrahedra on top and 4 tetrahedra below. So we will have 12 linear forms. If we assume that this is generic, that means all of them are different and they define different points, different 12 points in projective space in P2. So those points have this configuration. Is not generic, notice, because those points, for example, there are 2 triangles which meet, or actually not 2, for example, the 4 triangles that we have on top, they meet in a common edge. That means that if those points or these hyperplanes correspond to these points, so 1, 2, 3, 4, they are on the same line, because if you look at the original picture, these triangles have a common edge, right? So if a set of points in projective space are the dual picture of my partition for the splines, then actually this is going to be non-generic. Well, it will be generic if actually, for example, if you have a tetrahedra which is complete, which is just one plane, as if it's just 3 planes, intersecting, then certainly the picture is going to be generic, but this is just one case. In general, this picture is not going to be generic. So there are several results. Let me put it here. There are several results that relates ideals. So let me just point here. These are the this is the polynomial ring in 3 variables, just because we reduce one because all of them have the common vertex, and this is the ideal, which is generated by these powers of linear forms in 3 variables. This comes from splines, and this is isomorphic to the ideal of fat points, which is the ideal associated to those points in projective space of all the polynomials. So you define all for each point, you take all the polynomials which vanish up to certain order at that point, and you intersect all those ideals. Well, you have one ideal for each point, and you intersect those ideals, and you get an ideal which is called an ideal of fat points. Fat points, well, because you have they vanish, the polynomials there, they vanish up to certain order there. So there is a relation, or actually these two spaces are isomorphic. So we can compute the dimension of this quotient of this ring, if this module, if we compute the vector space, if we compute this, if we compute the dimension for the contract part of the dual part. There are several results which are for generic points in the projective space, not only for P2, which is our case here, but for Pn, P3, etc. And you can use those results in order to somehow prove some lower upper bounds and upper bounds for the dimension of the spline space. This is what I did at some point, but since these configurations of the points in projective space is not generic, it is better to use some of these other results, which is this work for particular points in P2. This, I'm going to, okay, I will finish on. So this is the approach we use to find this 3R plus 2 over 2. So there is something which is called the Walsh-Schmidt constant. This is for the ideal of fat points, and this gives is a constant associated to the asymptotic behavior of the minimal degree, so that the ideal of fat points of certain order is different from 0. Why do we care? Because there is a relation, as I said, between these fat points ideals and the dimension of the spline space, and we would like to see when this is 0, meaning when this ideal generates the entire polynomial ring. So we will be interested on when this part vanishes. The asymptotic behavior of this ideal is somehow related to the Walsh-Schmidt constant, and what we did was to compute that for our particular cases. Particular cases, it depends on the number of planes that meet a given vertex. So once you have all your dual construction, then you can use this. There is an inductive procedure in order to compute the dimension of these 5-point ideals. And this is, roughly speaking, what we use in order to compute this 3R over 2 or 3R plus 1 over 2. So what we did was to put a bound on this Walsh-Schmidt constant, and it follows then that the ideal generates the entire polynomial space when D is bigger than this 3R over 2. I think I have only 1 minute or so. There are several questions, and is that we don't know if under which conditions we have only a vertex star, so under which conditions we only have a trivial splines, meaning the splines is only one polynomial, so it's the same polynomial on each tetrahedra, or when we have something more and is given by this lower bound, correct? If this, we don't know under which conditions on the partition that happens for all t bigger or equal than 0, or which conditions on R, or whatever. Similarly, we have a question for that for closed vertex stars. We put this, let me just finish, I will not spend so much, limit 2 minutes. So we put all this together, so those results that I roughly explained for the vertex star, we put them together into, so this is the original formula for the general or generic tetrahedral partition. So when we have the problem more or less solved for this idea, which is solved well by using what I just explained for the vertex stars, and now we have the two homologies. So what we did was to compute a bound on these homology terms. And again, these bounds are, so we use some results by Michael Di Pasquale on counting these homological terms. These homologies are also the quotient of two of the kernel and images of maps. So it also has something to do with ideals of powers of linear forms and when you can have the entire ideal or not. Okay, we put a bound on that, and we compute a formula which gives the lower bound for any kind of for a generic partition for a D big enough. However, these are some examples. Let me just put it in the last slide. So this is some example. This not only works for tetrahedral partitions, but we can have some other polyhedra, as I said. And what we notice in the examples is that every time that the space, so this is the dimension of the polynomials, that if the dimension is given by this, that will mean that we don't have an interesting spline, that everybody has to be the same polynomial on each tetrahedra. This is a lower bound I compute using generic points. As I said, it's not very good. And this is the bound that we computed with Michael, which does not work really. The dimension is always positive, right? It's not that it's bad, but it's nothing that you will put there. It doesn't work if the degree is really small. But as soon as you go up, then, and actually you don't need to go that far, because every time, so here, sorry, the spline space, for example, if you take degree 4, the dimension is 35, which means, and this is the dimension of the polynomials in that degree, is the same as the dimension of the spline space. So even though our lower bound is not good, it actually, the space doesn't have anything interesting in it. If we go to degree 5, then the generic dimension of the spline space is 60, and the number of polynomials in that degree is 56. So that means that there are splines which are not trivial, and in that particular case, our lower bound gives the exact dimension. This does not happen only here, but happens in all the examples that we computed. And working together with people in approximation theory, so with Peter Alfred, with Larry Shoemaker, with Marisa Silben, we were talking together about this result. And using some tools with the Berenstein coefficients and the Berenstein-Bézier representations of splines, which is something they use in approximation theory, we were able to prove that actually D just need to be bigger or equal than 8R plus 1. Even though in the examples we know D can be smaller, but this is something we haven't proved. And these are just some references of some work that had been done recently on this direction. So these are the two results. This is for tetrahedral vertex stars. This is when we put it together for general, larger partitions in 3D. This is something similar, but for splines on oranges. That means that similar to the star of vertices, but you can have stars of edges of or a star of triangles in higher dimensions partitions. And this is just something completely different. It's splines, but you can also construct splines for patches, so that you don't need to have a fixed partition. You are very restricted if you do so. You will not be able to construct such it's a ball. It's like, actually these are splines constructed over a cube. You could not do that by starting from a 2D partition. So we also have results and very nice bases, also a construction for these kind of splines, which are co-geometrically continuous. So that's all. Thank you.
Thank you very much, Nelly, for your nice talk. Now we will pass the share for the session question to Felipe Rincon.
Yes, thank you. Maybe I can start by asking a question, Nelly.
Yeah.
For some of these results, you were saying that you need the simplicial complex to be generic, right? For the
Yes.
equality in the bounds. What kind of genericity conditions do you require? I saw that you said that, for example, the planes should be not parallel or things like this, but can they be very complicated genericity?
Okay, so there are two things. Yes, certainly we have some conditions when we prove the result with Michael, when we use this Wald-Schmidt constant, etc. And the conditions, there are some conditions that we have in mind that it shouldn't happen, but we don't have a complete classification of which conditions those are. So some of them are like, as you said, that sometimes when there is a plane, like a plane cutting the entire polyhedra, so there is something that the dimension goes up. So if you have something like that, certainly that will affect the dimension. However, when we put these results together with the people doing Berenstein-Bezier representation of splines, the results they have, it was like a recipe to compute the dimension, or to be more precise, a recipe to compute a basis for the spline space. And they did not have any genericity condition there. However, they did not have a formula. What we did together with them was to compute the formula, the number of basis functions that they had. The only bit that they couldn't compute was the dimension of the basis functions associated to splines supported on vertices, locally supported on vertices. And then we use the formula we had with Michael that it doesn't have any restriction. And what we found is that formula together, so computed the number of elements in the basis and putting it together with the dimension of the lower bound that we had with Michael at the vertex stars, that formula is exactly the same formula as we computed in the generic case. So actually, we don't have any generic condition after all, because if we put those results together, we prove that the lower bound works for any degree if the degree is bigger or equal than AR+1.
Thank you. I don't know if there are any other questions. Maybe I can also ask another question.
Okay.
A couple of minutes. On the other side of the spectrum, I imagine that in applications, the simplicial complexes that you deal with are really not generic, but they are constructed very. I don't know what kind of applications this is used to, but they must come with some construction that makes them not completely generic, but special. And in that case, like, are there results would it be interesting to try to understand these cases in particular? I don't know.
The generic ones in 3D?
No, the very particular ones, like the ones that arise in applications. I don't know, maybe it's a very regular subdivision of the plane that you just cut with parallel hyperplanes, or I don't know how these splines arise in practice. But I imagine there are cases where the simplicial complexes are not generic, right? Are very special. I don't know if there's some work in that direction.
Yes, is so in particular in 2 dimensions, so on triangulations, on triangulation, it is there are some regular partitions which are used, and the dimension sometimes is easier to compute. For example, when you have a line which go through the whole partition. Also, if you have a plane which go through the whole partition in 3D, then you know that you can have an extra spline. So you know that just for knowing the definition of the splines. But it is interesting to know which ones are all the possible non-generic configurations which happens in 3D, and we don't know which ones are those precisely. We know that if you take the degree is small, so if the degree is close to the order of smoothness, then you cannot apply these results because they have to be generic, and also other things go on. But we don't know which generic cases are those. So there is some intuitions of some of them, but as I said, there is not a general classification. Yes, in 2D, for example, the dimension formula, you take splines of degree less or equal than 3 and smoothness 1. We think that there exists a non-generic partition, that it should be similar, maybe, or not similar, but something like this. For example, sorry, let me come back. This is not the best way to come back, but okay. For example, these partitions are non-generic, and those are the ones giving counterexamples. But if you take degree D equal to 3 and R equal to 1, everybody is trying to find, everybody in splines is trying to find a non-generic triangulation such that the dimension is not given by that formula. Or in other words, we will also like to prove that for any kind of triangulation, the dimension is given by that formula. Actually, the dimension reduces to a very simple expression, like 3 times the number of exterior vertices plus 2 times interior vertices plus 1. But it will be nice to find a non-generic triangulations for which the dimension of the cubic splines, which are C1, is not given by that formula. And this is the kind of generic, this is the kind of non-generic partition. So you have edges which go through the whole, so they touch the boundary on both sides. These are different edges, but what makes it generic is that they lie on the same line.
Okay, thank you. So I think we'll move on to the next talk, right? Thank you, Nelly.
Yes. Thank you, Nelly, for your talk and for accepting our invitation. And also thanks, Felipe, for your support and for be part of the scientific board of this conference. We are ready for the next talk. And the next speaker is Elsa Lorenzo.
Okay, sorry, thank you, and bye-bye. Thanks a lot. Thanks, Felipe, and thanks all the organizers.
Hello, everyone. Welcome to the next talk of this conference. For this talk, we have Marlisha Sandoval Miranda as host. He works at the Metropolitan Autonomous University in Mexico and is member of the organizing committee. And whenever you want, you can start, Marlisha.
Thank you so much, Yuriko, and thank you so much, Elizabeth and Nelly. For me, it's a pleasure to be part of this conference with such as colleagues, women colleagues with outstanding careers like all of you. So, as Yuriko has said, I will introduce Professor Elizabeth Lorenzo. Elizabeth is an assistant professor at University de Neuchâtel. She has received multiple awards, including Golden Medal at the Olimpiada Iberoamericana de Matemáticas Universitarias, a Bronze Medal at the International Mathematical Olympiads, and a Woman Scientist of the month August 2019 of the UPWS. Her field of research lies at the interface between number theory and algebraic geometry, whose central axis is an effective approach to the algebraic geometric properties of algebraic varieties. Well, the title of her talk is Reduction of Plane Quartics and Cayley Octets. So thank you, Elisa, for being part of this conference, and go.
Thank you very much for the introduction, Lisbeth, and thank you very much for all to all the organizers for inviting me here to share my work with you. So as Lisbeth said, the title of my talk is Reduction of Plane Quartics and Cayley Octets. So maybe this looks like a very abstract thing, like for you, you don't know what is a plane quartic or why plane quartics are interesting, what is the reduction of a curve or what is a Cayley octet. But don't worry, like the goal of my talk is like to try to explain to you like all these objects and try to motivate why they are important. So just let me mention that this work that I'm presenting is a joint work with Raymond Van Mullen at MIT, with Jordan Dokin and Vladimir Dorkister at University College of London, and Ronald Lercier from Rennes. Also that the timing is kind of perfect because actually my collaborators are right now posting the paper in archive. So next week you will be able to look at the paper if you are interested. So let me start with the motivation. So I'm going to talk about reduction of curves and why is this like an interesting question like for me and for many people. So for this, I need to go back to the 1969, and to this theorem by Deligne and Mumford, in which they prove that the moduli space of smooth projective curves is irreducible. Well, genus greater or equal than 2 and over an algebraic closed field. Well, what is the moduli space? So what is this set? So this set is you fix a genus. So in some talks in this conference, we saw that curves can be classified by genus. So we fix a genus, we look at all the smooth curves, projective algebraic ones, smooth ones of genus G. We look at this set, and this set happened to be a moduli space. And then we wonder about the irreducibility, for instance, of this moduli space. There are many people that have studied like homological invariants of these moduli spaces. And one of these main results was again by Deligne and Mumford, in which this proved that this set, that is a variety, is irreducible. And the idea of the proof was actually compactifying this set. This set is not compact. So maybe, I'm talking about this like in a very abstract way. I'm going to give like more examples, precise examples later. Like for instance, if you work with elliptic curves, I have an equation. Maybe I can go here and show you the equation of an elliptic curve that will appear later. So elliptic curves, they are given by curves satisfying this equation. And you need like for the elliptic curve to be smooth, you need A and B to not satisfy a relation that would be like to be singular. So somehow this set of A and B's that parameterize the elliptic curve is not a compact thing. And the idea to prove the theorem of the linear Mumford is like to add like this extra object, like to compactify this set. So, I mean, we are not going very into the details of this theorem, but what is important, as I said, is like the compactification of this space. And for that, what we have to do is like to add like some points to this moduli space. And the points that we add are still curves, because this moduli space parameterizes curves, but they are curves that they are not smooth because they were not already considered. They are singular. But we don't want them to have like very ugly singularities. These curves that we add are what they are called stable curves. So what is a stable curve? So here we have the definition of what it is a stable curve. This is the formal definition. A stable curve here is a projective curve whose singularities are at worst double points. So they are not that bad. And they are not necessarily irreducible, so you can have like several components. But you ask, this is kind of a technical condition, the components of genus 0 to intersect the curve in at least other 3 points. So this technical condition, the intersection of at least 3 points, actually can be translated into saying that you want that the automorphism group of the curve is finite. So this is just a technical condition. So yeah, basically in practice, what does it mean? It means that you have like curves like the ones that I'm showing here. So you have, for instance, a genus 0 curve with some nodes as the first one that I'm showing. Maybe you can have also something that is like non-irreducible, so reducible. So you have 2 components. For instance, one component of genus 1 and one component of genus 2. Notice that these singular points actually count as multiplicity 2. So for instance, in this example, this genus 0 component is actually intersecting the curve in 3 points. So the point in which is intersecting the other component, and then the double point in which is intersecting itself. And then, for instance, you also have the third example is a smooth curve. So all those 3, they are stable curves. And as a corollary of this theorem that tells you that the moduli space is reducible and you do it by compactifying with these stable curves, you get that every curve defined over a local field acquires a stable reduction over a finite field extension of the base field. What does it mean? Again, I wrote like the abstract statement, but what does it mean? It means that when you have a curve and your curve is given by some equations, and you want to do, for instance, imagine that your curve has integer coefficients, and you want to know, like, if your curve that was like a nice smooth curve, if you look at it now modulo p, a prime number, what is happening with your curve? So this theorem is telling you, okay, if you just work with the equation that you are working, maybe you do the reduction and you get a very ugly thing. I'm going to show you like some examples now of reductions. But you can find a model that is actually like the best possible one, that is this stable reduction thing. So this is like the best possible model. So you can find this best model in which when you do the reduction, you are going to get at worst a stable curve. That is a curve with mild singularities, the ones that we described before. In order to do that, there is a price to pay. That is that maybe you have to go to an extension of the base field. So I'll do like a precise example later. But the funny thing is that this minimal, if you take the minimal one, it is unique. So the minimal one is unique. So maybe I should have said that before, like, yeah, the reduction depends on the model. So we are looking like for a nice model. So here I have a kind of a basic example to show this. Imagine that I'm working with this curve, the one that you have here, F1. So this is like a nice conic. And if I do, for instance, the reduction modulo 7, I still get a nice conic. So I would say that this conic has good reduction, modulo 7. But now imagine that I'm very naive and I'm looking at my conic in this way, with this equation, F2. So this curve given by F2 actually is isomorphic to the one given by F1, right? If you want, I just multiply each variable by a square root of 7. So, I mean, if you want even to stay in the field, I can write it like this. I just multiplied each variable by 7. So if I work over the rational numbers, I'm not really changing anything. I can divide and multiply by 7. But now the problem is that if I want to do the reduction modulo 7 of this model, actually this equation becomes 0 equal to 0. So the variety that this ideal is defining now actually is all P2. So I mean, this one, a conic is isomorphic to P1. So I get something different. And well, also like in this third example, if I multiply, starting again by the first equation, I multiply the variable x by a square root of 7. So I mean, again, these two curves, F1 and F3, they are isomorphic. So I mean, over the rational, well, yeah, I'm going to write again a square here. So then the chain of variable is over the rationals. So over the rationals, like these two curves, they are isomorphic. They define the same curve, right? But when I do the reduction modulo 7, I get something different. And what I get different here is that if I do the reduction modulo 7 of this, then like I only get this part. The other part goes to 0. So basically, I'm getting like 2 lines. So here you have an example of how like the same curve, if I take different models, I can get like different reductions. So, I mean, in this case, the most beautiful model, the nicest one, would be the first one. Okay, so when we want to look for the stable model of a curve, what we want to look is for the nicest model. So, okay, that was kind of an easy example, maybe too easy. So now let's try to do like a little bit more difficult example. So I want to work now with a curve of genus 2. So look at this curve given by this equation. So and assume that P is a prime, that I want it to be different from 2. Because curves that looks like this, modulo 2 doesn't work well, don't work well. So I assume P to be different from 2, and I want to look what I get when I do reduction modulo P. So, I mean, I can tell you that actually what I get is, thanks to this fact, I mean, actually I know that equations given by this shape, they are smooth if and only if the polynomial f of x doesn't have any repeated root. And in this case, if you do modulo P, the equation that I started with, right? If I do modulo P, basically I'm like killing this term, then I get that 0 is a multiple root. It is even a triple root. And actually this means that I get like a really ugly singularity. I'm getting something like this. And this is not a stable curve, because for a stable curve, I want at worst like nodes. So like singularities of order 2, let's say. So, okay, I have the genus 2 curve given by this equation. It's an ugly equation. I mean, it's an ugly, if I just do the reduction, I get like an ugly thing. I want to look for a better model. So what is the idea here? Well, here you will see the computations are kind of ugly too, but the result will be nice at the end. So the first thing that I do is like this first chain of variable. And if I do the chain of variable, and then I do the reduction modulo P, I actually get this equation. And this equation is the equation of an elliptic curve. So somehow I get like kind of one component of the reduction. But now if I do this another chain of variable that is more sophisticated, here they are like powers of P that appear here. I get this equation, this one. I can divide all this equation by P to the 6. And then if I do the reduction modulo P, I get this equation. So I get another elliptic curve. So basically these are like different charts that I can get of my curve. And when I do the reduction, I get like different components on the reduction. And I mean, if you take like, you make the computations little by little, what you get is that actually the stable reduction for this curve, I mean, you have path reduction, but you get like 2 components, 2 elliptic curves intersecting at a point. And actually, you can see that this point actually corresponds from the original model to this point. So this one would be like what is called like the special fiber of the stable model. That is what we usually call, in other words, the reduction type. So, I mean, this is the definition of the reduction type of a curve. So we just saw in the examples, when you have a curve, it depends on the model, you get like different possibilities for the reduction, but there is one reduction that is like the nicest one, that is the one that corresponds to the stable model. And this one is, well, I mean, it's a special fiber. The special fiber is because when we think about a model, we think about a scheme. We don't need to go into the technical details. Just for you, for giving like the definition of what we call the reduction type. The reduction type is like the nicest reduction that you can have for a curve. And it's a reduction of this stable model. The problem is that what is a stable model? The stable model is like all these equations, like all these equations that I wrote here, like together, all those chains of variables. And well, the conclusion is that this is something that is like complicated, right? I mean, all these equations that I wrote it down, it's really complicated. Somehow the idea is that you have to start to do like blows up of the singularities of your curve until you get something that is nice. But there is not really like like a structured algorithm. Well, I mean, the algorithm is just do resolution of singularities. But again, this is complicated. As you saw in this example, that is kind of an easy example, but already it starts to be complicated. So the general question that many people asked is, how can we determine the reduction type of a curve, so like the nicest possible reduction of the curve, without really having to compute the stable model that is like all these set of equations, chain of variables, resolution of singularities. Like if you just want to get like, yeah, tell me what is the reduction type, the nicest possible reduction that you can get. So this has been a question that many people have been interested in and try to solve for different families of curves. So maybe before I tell you my results, I want to tell you a little bit like the state of the art of this question. So like the first case is the case of elliptic curves. So in 1975, Tate got this result. So, well, I mean, he also did the cases of characteristic 2 and 3, but because it's easiest to state the result when the characteristic is different from 2 and 3, I'm going to restrict myself to this case. So we start with an elliptic curve that is a curve given by this equation when the characteristic is not 2 and 3. And now if we just do like the naive reduction of this model, we can actually get like 3 things. We can get that we still have a nice elliptic curve, so like a curve of genus 1. Or it can happen that I have some singularities. I can have like just a node, so this would be like a nice singularity, or I can have a cusp, that this is like an ugly singularity. And what Tate's proof is that actually when you are in this third case, if you allow yourself to go to a field extension, you can find always a better model that is in this case or in this another case. So basically for elliptic curves, we only have 2 possibilities, right? We have good reduction or we have bad reduction. And Tate actually described these 2 possibilities in a really nice way. Basically, Tate tells you, you just have to look at the valuation. So this is like the power of P that divides the J invariant of the elliptic curve. The J invariant actually is given by this formula. So, I mean, I guess that many of you already worked with elliptic curves. If you didn't, doesn't matter. It's just like this polynomial expression of the coefficients. So basically, Tate's criterion is very easy. You just look at this number, you look at how many powers of P you get, and depending on how many powers you get, you can determine if you have good reduction or bad reduction. So it's like a very explicit, nice criterion. Okay, so this is for elliptic curves, that they are curves of genus 1. What can we say for genus 2 curves? So for genus 2 curves, we have a result given by Liu in 1993. Genus 2 curves, they are what we call hyperelliptic. So they are also given by equations that looks like this. So y squared equal to a polynomial on x. And this time the degree of the polynomial is 5 or 6 in order to get that we have genus 2. And like the possibilities for the reduction of a genus 2 curve are actually the 7 possibilities that you have here. So you have like, you still have a genus to curve. Then you can have a node like here, like in this case, or you can have that it splits like in two genus one components. That was like the example, this one here is the example that we saw before. Or you can get like other singularities, like in here, that you got like a double node. Or you can get, I mean, you see that you can degenerate like in a different ways. And somehow, I mean, this degeneration also goes into the direction of compactifying the modular space. It's like, you know, like you are getting to the border, like in a different direction. Well, the thing is that Liu worked out the case of genus 2 and determined in terms of the, determine the reduction type in terms of the valuations, again, of some invariants that we associate to genus 2 curves. They are called Igus invariants. So it doesn't matter who they are just like polynomial expressions on the coefficients of the curve. And he gives, again, like a very explicit criterion just by looking at the valuation of those invariants to determine the reduction of the curve. So it's a beautiful result. The only problem, let's say, with this result is that it is totally ad hoc, meaning that, I mean, we cannot really generalize it to other curves. Like he really works with the model of the curve, makes the computations, do the resolution of singularities, and computes the things. So, I mean, the paper is a lot of computations that at the end he managed to put like in a nice way that you only have to look at the evaluation of the invariants, but we cannot really generalize the result. So other cases that they are kind of known are for superelliptic curves. That is kind of a generalization of a hyperelliptic curve. But this result is more like the general theory. So Irene Bau and Stefan Bevers in 2017, they gave kind of a theory that applies to all those curves. So you can apply this theory to each curve one by one. And then like some people, Tim and Vladimir Dotkister, Céline Mestre, Adam Morgan, they also gave like an algorithm more detailed for this case, so the superelliptic case with L equal to 2, so the hyperelliptic case. So they gave like an algorithm, really nice, to describe like the reduction type, and actually they worked out like the details for genus 2 and genus 3. And it's quite nice because basically this paper used what is called the machinery of the cluster picture that basically tells you, I'm coming back to the genus 2 case to do the example. We know that if we have a polynomial of degree 6 with the 6 roots that I'm writing down here, no, this is 5, 6, you get a curve that is smooth if the 6 roots, they are different, modulo P2. But now, I mean, I started with my 6 different roots, I looked modulo P, I can get that some of these roots become isomorphic modulo P. And this is why I get something that is not smooth anymore. And basically, they explain all these possibilities for the reduction type of a genus 2 curve, but looking at how the roots collapse modulo P. And you get a dictionary. So, I mean, what you have here on the left, the reduction types, actually corresponds to the following, what they call cluster pictures. That means like how the roots collapse modulo P. And it's really nice because, I mean, you can really see how the cases degenerate by looking at these degenerations. So, I mean, with this theory, we can explain like, or we can compute the reduction type of all the hyperelliptic curves just by looking at these cluster pictures. So, I mean, it's a really nice result. But, I mean, it only works for hyperelliptic curves. There are curves that they are non-hyperelliptic, right? Then, I mean, with some collaborators in these papers, we tried a new approach that is called the admissible cover approach that in our case worked well to work with cyanic quartics. So cyanic quartics, they are a special type of genus 3 curves. They are non-hyperelliptic, so it's more generic than the hyperelliptic case, but still, they are curves that they have like extra automorphisms. And basically, they have the property that when you do the quotient of your curve by this extra automorphism subgroup that you get, well, you get like some nice properties. So this would be for another talk, but I have like nice pictures here. Actually, I enjoyed a lot this paper because there were a lot of nice pictures. So basically, the idea here is that you start with your genus tree curve, and you have like a map of degree 4 to a genus 0 curve that is like this quotient that I described. It ramifies at 6 points that they are paired up. So I have to blue, to red, and to green. And then basically what you do is like you study like the reduction of the genus 0 curve with the marked points, what we call the decorated graph. And then from there, you can get the reduction type of the curve. And actually, I didn't write it, but you get like several genus 0 components intersecting in a well, nice way. But again, like for this approach, you need to have extra automorphisms, and this is not always the case. So, well, now before I go to the general case, the last work that I want to mention is by Tim Dotkister, in which he gave an algorithm, to compute like the reduction type of plane curves, but with some restrictions. Like you need the singularities to be well placed and not having so many singularities, because otherwise everything becomes a mess and the algorithm doesn't work. But I mean, all this is just for saying that many people got interested like in this problem, and that we know how to answer the question about computing the reduction type for many families of curves, but that we still have this question about, okay, what happens for the general case? Or, okay, if we can do the general, we cannot do the general case. By general case, I mean a curve of genus G with not special symmetries. What can we say for the generic genus tree case? So non-hyperelliptic. And this is the case that I want to handle in this talk. So a generic genus tree curve is given by a plane quartic. So by an equation like this, where the degree of f is equal to 4. So this is a case that I want to work with you today. So, okay, the idea is that we have this cluster picture approach that works for hyperelliptic curves, and that somehow we would like to mimic for the general case, except that we don't have these extra automorphisms. So what do we do? Well, the idea is realizing that somehow these cluster pictures, the ramification points for the hyperelliptic involution, that they are like the roots of this polynomial, they are kind of related with the two torsion of the Jacobian of the curve. So you don't know what it is, it doesn't matter, but it's related with the two torsion. And what do we know about the two torsion in plane quartics? So we know that the two torsion of plane quartics is kind of related with bitangents. So what is the bitangent of a plane quartic? So it's a line. So a plane quartic is degree 4, right? So if I take a line, generically, it's going to intersect the plane quartic in 4 points. But now, I mean, so generically, it's going to do something like this, right? So I get 4 points. But there are like some special lines that cut the quartic in only 2 points with multiplicity 2. So those are the bitangents. And in general, a plane quartic has 28 bitangents. And basically, this is special because in terms of divisors, we get that the bitangents define things that twice are equivalent to the canonical divisor. So this is related with the two torsion. If you never heard about the divisors, two torsion, whatever, don't worry about it. Just think about the bitangents of the plane quartic. So yeah, I mean, we think, okay, this can be something that we can look at it. At this kind of two torsion thing of the plane quartics. And actually they are related with these bitangents, they are related with what is called the odd theta characteristics. What is a theta characteristic? Well, it teaches a divisor that twice is equivalent to the canonical divisor. And it's called odd because the associated Riemann space has odd dimension. If it got even dimension, it would be called even. And those theta characteristics, I mean, they are nice because, I mean, those appear a lot in the literature, like in the classical algebraic geometry of plane quartics, like already like in the 19th century. People like really work with plane quartics, bitangents, and I mean, all this kind of classical geometry. So people understand this well. And well, when you choose like 7 among these 28, you take 7 of them like well chosen. Those define what is actually called an Aranjol system. Maybe some of you heard about this. And well, I mean, it's nice because just with these 7 bitangents, you are able to recover the curve. Given the curve, you can get the 7 bitangents. So I don't know, that was like our first guess, like, okay, maybe this is going to be like the equivalent for the cluster picture. We can look at the bitangents of a plane quartic and look at how they collapse modulo P and see if we can say something about the reduction type. And well, we did a lot of numerical experiments, and I can tell you that we failed. It doesn't work. That was like the first approach, and it didn't work. So we had to think harder about something else. So we said, okay, so looking at the odd theta characteristics doesn't work. Let's look at the even theta characteristics to check if it works. So again, we went back to the classical algebraic geometry, and we found some constructions by people in which, when they were taking an even theta characteristic, there are 36 of them, so it's more than 28. For the ones that know about the two torsion, if you do 28 plus 36, you get 64. That is 2 to the 6. That is actually 2 to twice the genus of our curve. So, I mean, just to convince you that this is really like the two torsion of the abelian variety associated to the curve. Anyway, if you don't know what it is, it doesn't matter. If you take for each of one of these 36 even theta characteristics, you can define an embedding of your plane quartic that lives in P2 into P3. And then you get like an ugly equation. But many people studied this because via this embedding, you can define actually what it is called a determinantal. This, I'm not going to use this determinantal expression, but it's something that is kind of nice and many people studied in the past. You can write your plane quartic as the determinant of a matrix in which you have x, y, and z in the variable. So I mean, it's kind of a fancy thing. And again, like many people in the 19th century studied this kind of determinantal representations of plane quartics. So I'll just give you like some references. And also, if you want like a more modern reference, I can suggest a paper by Polman, Stormfeld, that was actually also mentioned in Jonathan's talk yesterday. So it's a paper from 2011 in which they study also these determinantal representations. And well, the funny thing, I don't care like in this work about the determinantal representation, but I care about the following, that when you consider the equation of your curves in P3, and you also look at the bitangents in P3, so you get 28 lines. These lines, they intersect at 8 points, and actually these 8 points determine the 28 characteristics by tangent, sorry, because, well, I mean, if you do 8 over 2, you get 28. So your 8 points give you 28 lines that happen to be the bitangents of the curve and determine the curve. And these 8 points that give you, in a weird way, but give you a plane quartic, actually we figure out that is like the right object to look at the reduction of plane quartics. So let me give you like some definitions. So Cayley octet, that was like a word that appeared in the title of my talk. A Cayley octet is by definition a set of 8 points in P3. So it's an octet is 8 points in P3 that they are given by the intersection of 3 quadrics. Well, these 3 quadrics are actually the 3 quadrics defined by A, B, and C. And it is said to be regular if it satisfies the following three conditions. No 2 points coincide, so I have 8 different points. No 4 of them lie on the same plane, so they are not coplanar, and the 8 of them do not lie on a twisted cubic. So this is the conditions to be regular. And if you want, the property about being the intersection of 3 quadric is just given by some equations. Okay, so this is given by some polynomial equations, and basically can be just translated into the condition that any 7 of them determine the 8. So basically, you can think that you are actually working with 7 points instead of 8. And actually, these 7 points are in correspondence with the rank hole system that I mentioned before. So it's just different representations of the same thing. And the funny thing is that we have like this correspondence that is the same thing talking about a smooth plane quartic once that we fixed an even theta characteristic, that is the one that gives embedding, and giving a regular Cayley octet. So there is this magical correspondence. So I want to compute the degenerations, so like the singularities that I can get when I start with a plane quartic. And we are able to translate this into looking at the Cayley octet, so these 8 points in P3, and looking at how these 8 points degenerate. And degenerate means that if I was starting with things that didn't have like points colliding or didn't have like points in a plane, now when I look modulo P, maybe those points collide or become coplanar. Those degeneracies are going to tell me about the singularities that I get on the curve. So, I mean, I get this nice correspondence. So in order to measure the degenerations that I get in the Cayley octet, I'm going to look at some valuations again. So let me give you the following definition. Given an octet, so basically given 8 points like this, I'm going to define the valuation data associated to this 8 point as follows. It's going to be a function that goes from this set to the rationals. And who is this set? So this set, basically, I'm going to consider all subsets of 4 elements in the indexes. You will see why 4. Recall that my points live in P3, so they have basically 4 coordinates, each of them. So basically what I'm going to do is like to each subset of 4 indexes, I'm going to associate the valuation of the determinant made, of the determinant of the matrix made by these 4 points. So basically my octet is 8 points, and I can take 4 of them. I can make a matrix with these 4 points because they have 4 coordinates. So I have a square matrix of side 4. I look at the determinant, and this determinant a priori is going to be non-zero because no 4 of the points are coplanar. But now when I do the reduction modulo P, those points may collapse or may become coplanar. So I can have like a positive valuation of this determinant that is measuring this degeneration. And then I have like an extra valuation that is what I call the twisted cubic index. So it's the valuation that is going to tell me modulo P this condition, if the 8 points lie on a twisted cubic. So I define this. Like starting by my octet, I look at these valuations. And now I can tell you this is our main result, that maybe you're going to be a little bit disappointed because our main result is actually not a theorem, but a conjecture. But you will see that it's a really nice conjecture. So this is our main result that we are going to read together. So our main result is the following. You start with a smooth plane quartic. Over a non-Archimedean local field, maybe this is scary. Just think, if you want, about the rationals. You have integer coefficients and you're going to do modulo P and you want to check what you get. P different from 2. This is because, again, the 2 torsion is involved, so we don't want P equal to 2. And associated to our plane quartic, we take a Cayley octet. So this means that we made a choice of even theta characteristic, but it doesn't matter. You can take whatever you want. So you just take a Kiley octet associated to your smooth plane quartic, and what we conjecture is that the valuation data, that is the set of valuations that I just defined before, associated to the Kiley octet of your quartic, completely and explicitly determines the stable reduction of your plane quartic. And this explicit is really going to be like really explicit. I'm going to give you now like the explicit version of the conjecture, like how you read the stable reduction, the reduction type of your plane quartic by looking at this valuation data. But before that, I mean, I want to convince you that this is something that is difficult to describe, because the Kiley octet, as I said, is not unique. And there is the axiom of different groups on this Kiley octet. On one hand, we have like an easy axiom of S8 because I have 8 points. And actually, I don't care about the order of the points, but I'm working with them as a vector. So somehow I'm giving to them an artificial order, but I'm telling you that this order, it doesn't matter. So this is like an S8 axiom. Then we have a Cremona axiom that is called Cremona because happens to be like a Cremona axiom in P3. But basically, this Cremona axiom means that I have the 36 possible choices of the even theta characteristic. So I can get like different Kiley octets. And then, of course, I have a PGL3 axiom that is coming that I can do like linear chains of variables. So the Kiley octet is not that well defined, let's say, starting from a plane quartic. I can get like many different octets, but they are actually equivalent. Well, just to mention that these two axioms together actually give a symplectic axiom. So this is again related with the torsion, but it doesn't matter. Okay, so I wanted to convince you about that. So that the valuation, so I'm going to define the valuation later, that is like a difficult object to play with. But maybe let me show you before, this is a nice picture, all the possibilities for the reduction type of a genus 3 curve. Remember that for an elliptic curve that is genus 1, there were only 2 possibilities. For genus 2, there were the 7 possibilities that Liu computed. And for genus 3, surprise, I'm going to show you. This is the graph that you get. So this is for the non-hyperelliptic case. And this is for the hyperelliptic case. There is a little bit smaller. But for the non-hyperelliptic case, actually, you have all these possibilities. There are 42 possibilities. So basically, we are looking to distinguish these 42 possibilities for the reduction type of a plane quartic. So you can imagine that there are a lot of computations in the middle. And the thing that I was saying about the axiom here just before is that the Kiley octet is not that uniquely determined. So I'm going to give you like some examples about this axiom and how the valuation of the Kiley octet changes. So let's look at the valuation data of some Kiley octets and how this valuation data changes by the action of those groups. So in this example, I start with this octet and I wrote my points like in columns. So I took my 4 points like the canonical one, the fit one here. So I can do always like a linear chain of variable, like to get like 5 points in a nice way. And then I'm going to get this point, for instance, which coordinated 1 to P, 3P, 4P, and then 2 other points that I just assume to be like in a generic position, that everything goes well with those points. So what happens if I do the reduction modulo P of this octet? Well, if I do P modulo P, basically this becomes 0, this becomes 0, this becomes 0. So basically I get that these 2 points collide modulo P. Sorry, these 2 collide modulo P. Okay, so this is something that can happen. But now I'm going to make a transformation on this Kiley octet. This transformation is going to be a linear transformation in which I'm just going to multiply the first coordinate of all the points by P. If I do this, then my Kiley octet becomes this one. Like for the first one, I multiply the coordinate by P, but because it is a projective point, I can divide all the coordinate by something. So I get still the first point. Here we had 0, so it's okay. For this point that was a 1, 1, 1, 1, I get a P. For the second point that it was this one, so I would get P to P, 3P for P, but because it is a projective point, I can divide everything by P. So I get 1, 2, 3, 4. And then for the other 2 points, I get just the P in the first coordinate. What happens now if I do modulo P? So basically that I get a 0 here, I get a 0 here, and I get a 0 here. So basically what I get is that this point, this point, this point, this one, and this one. So these 6 points become coplanar. So somehow I want to consider that 2 points colliding is the same thing that 6 points becoming coplanar. So, and of course, the evaluation of these things are different. So there is a lot of combinatorics and a lot of things that you want to consider equivalent. I'm going to give you the answer after this, but I mean, I just want to show a little bit that the computations actually can become like really complicated. And now, of course, I could also apply a Cremona transformation that add in a fancy way, leaving the first 4 points invariants, but transforming the other 4 points in a certain way. And this time what I get is that there are 4 points that collide. In this case, like this point, and this point, and this point become equal modulo P. So, well, this I was just trying to convince you that this becomes complicated. And I'm going to show you which ones are like the blocks, like the building valuations or building blocks to describe like how an octet can degenerate. Like for the cluster pictures, you saw like the degenerations just were like point colliding. Like I'm going back to the example of genus 2. Here, right, we just had like clusters here of site 2 and clusters of site 3. And now our 8 points in P3 can degenerate in many ways. And I'm going to show you the blocks in which we describe the degenerations. So we have this complicated but nice diagram in which we have first what we call alpha blocks, and that they are going to correspond to the degeneration of the curve producing a node. And they are given by getting like 2 points that collide, as in the previous example, or 4 points becoming coplanar. And this can still happen in many ways, but all the equivalent things are described by these 2 objects. Then we have the chi blocks that corresponds to having a component of some genus, G, that splits into 2 components of genus 1 and 2, such that G1 and G2 is equal to G. And again, this block up to Cremona transformation, after to linear transformation, and up to permutation of the points can look in many different ways. Then we have 5 blocks that corresponds to also kind of a complicated thing. That is when we have something that looks like this and becomes something that degenerates like this. This is genus G1, genus G2, with G1 plus G2 equal to G. And then we have a 4th block that they are the hyperelliptic blocks that basically corresponds to start with something that is non-hyperelliptic and that becomes hyperelliptic. So basically we have this kind of 4 different blocks in which an octet can degenerate, having these blocks. We can like build this block together, as in the hyperelliptic case, we had the cluster of site 2 and 3, I'm going back to the example, that they could live together. And if you want here, an observation is that you can have like 2 things like this, for instance, but you cannot have 2 things like this, right? Because basically one cluster of site 2 here means that these 2 points becomes congruent modulo P, and this one would mean that the second and the third also becomes congruent modulo P, but then necessarily I have that the first and the third becomes also congruent modulo 3. So this is something that I cannot have. I could have this, right? So not all the blocks can be combined in a compatible way. And we have the same thing for our blocks, that they are like much more complicated. So we have here a table that tells us which kind of compatibility is possible. For instance, we can have like two twins like this, but we cannot have twins like this. So we define all these compatible configurations, and well, our conjecture, I'll just show you like the result, is that the different reduction types that we list in these columns are associated to the following generalizations of the cluster pictures, that for us is the octet picture, saying how the 8 points can degenerate and collapse. And for each type, we actually have like different equivalent possibilities. So the order of pictures, they are really nice, but as you can imagine, this is really like a mess. And maybe because, I mean, I don't know how much time I had, but I want you to have time to ask questions. So I'm going to skip how to generalize G to any genus. So you can ask me this as a question. I'll just pass to tell you what we can prove about our conjecture and about how this, how we got this conjecture, this result. So basically, our conjecture is that we have on one side all the possibilities for the reduction type of plane quartics, and on the other side, we have all these possible octet pictures. So waiting with the octet can degenerate, and we made a one-to-one correspondence between these octets and these degeneration types. So we cannot prove it yet, but we conjecture that this is true. Why? And well, the answer is that we produced many families of plane quartics for which we knew how to compute the reduction type with the Tin-Dotkister machinery or with the Harris-Morrison method of doing blowing ups. So we really did like a lot of experiments, like numerical experiments. Also, like for some specials plane quartics, as the super elliptic ones, the hyper elliptic ones, the Chiani ones in my previous paper, we know how to compute the reduction type. So basically, we tested our conjecture and we elaborated our conjecture by looking at thousands of plane quartics for which we knew how to compute the reduction type. And then we got this, this conjecture that we really believe that it is true. But can we prove something that supports our conjecture? And the thing is, yes, like for some cases in which there is not that too much degeneration, like the smooth case, the hyperelliptic case, only one node or only one intersection point like this, we are able to prove it. We are also able to prove that the different configurations that we saw associated to its curve, they are really equivalent and that the axiom behaves well. And we have like some ideas about how to prove this, but this will be like for a second paper that is probably coming up like later, not soon. And well, I think that even if I started late, I prefer to stop here so you can ask me questions. So thank you very much for your attention.
Thank you so much, Elizabeth. This is a nice talk and an interesting topic. So some comments or questions for Elisa? You can write on the chat if you want, or yes, we have a question on the chat. I think everyone we can read it. The question is from Carlos Barco. A question: which will be the limitations of mentioned Gusa invariants in the context of studying the reduction of plane quartics?
Thank you very much for the question, and it's very interesting. So for genus 2 curves, we have the Gusa invariants, that are the invariants that Liu uses to describe the reduction type for genus 2. Gusa invariants only work for genus 2, but then for genus 3 curves, we have something that they are called Dix-Meron invariants. And actually, this is something that we would like to do. This is the what next. That is actually to be able to describe this reduction type, not by just looking at the octet picture, but just by looking at the evaluation of some invariants. So, well, I mean, so if you want, the limitation is that Igusa invariants are only for genus 2, but there is an equivalent object, or they are equivalent invariants for genus 3, that they are the Dix-Meron invariants. And we could try, and we would like, and we already started to think about it. So hopefully we'll be able to generalize this for plane quartics.
So thank you so much, Elisa. Someone else have a question? No? Well, I just have a maybe it's a basic or simple question, Elisa. For students, if they want to immerse in the study of Cayley octets or octets diagrams, what's the bibliography or way that you recommend?
Well, first, of course, I can do like publicity to myself. So next week in archive, you will get like the preprint of this article. But then, I mean, I can really maybe insist, because it was a beautiful paper to read with the connection of the Cayley octet determinantal representation. So the paper by Stormfels, this paper. So it's Polman, Sturfel, Vincent from 2011. Well, if you Google Cayley octet 2011, probably you will find it. It is on archive. And it's a beautiful paper in which you have like all the history behind the classical geometry and the Cayley octets, plane quartics, bitangents, and computational approach to this problem.
Well, thank you so much, Elisa. We are with our students. So hello.
Okay.
For Mexico. So thank you so much for being part of this conference. We say in Spanish, aplausos.
Gracias.
Thank you so much. I think we are on time. So we have, I think we should go with our next speaker. And
okay, well.
Arturo.
Hello, everyone. We are ready to the next talk. We have as host to Duban Cardona. Duban is president of the scientific board of ICM-AM Latin America. And Duban, please.
Okay, so it's my great pleasure then to introduce our next speaker. Please let me say something about Emmanuel Carneiro. Emanuel Carneiro is a mathematician from Brazil, working in the fields of harmonic analysis and analytic number theory. In 2005, he got his bachelor and master in mathematics from the Federal University of Ceará in Brazil. In 2009, he got his PhD in mathematics from the University of Texas at Austin. Very remarkable, maybe to say that in 2010, from 2009 and 2010, he was member of the Institute for Advanced Studies in Princeton. Later, he moved to companies from 2010 and 2011. He was associated consultant at McKinsey & Company. From 2011 until 2018, he was associate professor in IMPA in Rio de Janeiro, Brazil. And from 2018, he's a research professor in ICTP. So we are very happy to have you today, Emmanuel, who will talk about Fourier analysis and the least quadratic norm residue. So, Emmanuel, please start.
Thank you, Duvan. Thank you, Yuriko, for the nice invitation. It's a pleasure for me to be here with you all. I hope everybody can hear me and see me fine and see the slides. If you have any trouble, you can just jump in and if you have any questions, okay, during this conversation. I know it's Friday night for me, Friday afternoon for some of you, Friday morning for some of you. So, but anyway, it's a Friday, so I want to be very light so we can have a light conversation now and hopefully talk about some Fourier analysis and number theory, okay? Let's see. This is the title, Fourier optimization and the least quadratic norm residue. A little bit of an introduction. So if I would have to describe myself, I mean, I would say that I work mainly in the field of harmonic analysis, which is concerning the mathematics behind understanding all sorts of oscillatory phenomena in nature, right? But I like to kind of, it has relations to many other fields, such as approximation theory, number theory, PDEs, probability, and I like from time to time to explore these connections, especially connections related to number theory, which we're going to talk about today. And within this context, I'm particularly interested when some sort of extremal phenomenon happens, you know, try to find the sharp form of a certain inequality, trying to find the optimal approximation of some sorts. You know, these sorts of questions drive a little bit of my research in this field. Let's see. So there's a very famous book which serves as an inspiration for us. It's this classical book by Hugh Montgomery, 10 lectures on the interface between analytic number theory and harmonic analysis. If anyone is interested in learning a bit more, this is certainly a good place to start, you know, and you can see some examples. And everything that I'm going to talk today is based on this joint work with my three co-authors here, Micah Milinovic from the University of Mississippi, Antonio Pedro Ramos from CISA, and Emily Quezada Herrera from the Technische Universität Graz in Austria. All right. And the basic plan for today is the following. This is a conversation. This is supposed to be a light conversation in analysis and number theory. And I would like to discuss with you today two problems in analytic number theory and one problem in Fourier analysis. And I want to show how these three problems connect, you know. And I'm going to try to keep the focus on the big picture. I know we have part of the audience interested in algebra, in combinatorics. So I would like to make it in a way that everybody understands most of it, or at least part of it, you know. And the focus I like to call on how we arrive at this Fourier optimization wonderland. That's how I like to call this philosophy. Okay. So there's something I like to call a Fourier optimization framework. And this is the following. Sometimes you have a problem in number theory. You're kind of investigating an inequality in number theory or some situation in analytic number theory, and you believe that Fourier analysis might be interesting for that problem. So what can you do? Well, it turns out that sometimes you're able to design a certain Fourier optimization problem connected to your number theory problem. If you can do that, that's some sort of a proof of concept that Fourier analysis might be relevant to understand that number theory problem. Well, when you have a Fourier optimization problem, what you can do is you can try to solve it. You can try to find the function that does the best job that you want it to do, the extremizing function for that optimization problem. You want to find the answer and the possible extremizing functions. This turns out to be usually hard. You cannot always find and pinpoint the extremal functions or find the value of the sharp constant. So sometimes you can at least try to find a good approximation for the solution, or you can try to find a near extremizer. Okay? And then once you have done this, well, you can kind of evolve your Fourier optimization problem towards designing, what should be the correct one, because sometimes you set up an original problem, but then you realize a posteriori, you realize later that you could do better. You could weaken your hypothesis, you can enlarge your class of test functions and so on, and you can generate a new, Fourier optimization problem. And you can keep doing this until there is a force coming from the other side saying that you have reached a threshold, you have reached the barrier, If you want to understand one example of how this Fourier optimization framework works, is in this recent breakthrough in the sphere packing problem that the Wiazowska got her Fields Medal mainly for. If you know the history, there is certain, you want to find bounds for the densest packing of spheres in RD. There was this nice paper of Kohn and Elkis in 2000, relating it to a certain problem in Fourier analysis, and optimizing this problem in Fourier analysis would give upper bounds for the sphere packing density, and so they improved the current upper bounds in all the dimensions up to 36 with this method, and they noticed that in two particular dimensions 8 and 24. Their upper bounds that they were getting with this method were getting actually very close to the known examples. And so they conjectured that this was the correct Fourier optimization problem in these dimensions, in the sense that if you could really find the optimal functions, the extremal functions for this Fourier optimization problem, you would match and you would solve the sphere packing. At that time, they just had approximations of the best constant. They just had near extremizing by using computational sophisticated programming tools. And what Wiazowska did was use Fourier analysis with a little bit of modular forms to actually construct and prove the extremal functions exist, and they were given by a certain magic functions that actually matched the conjecture, right? So this was kind of an example of this Fourier optimization framework, where you see that in step 3 here, this is the correct one because there is a force coming from the other side saying, namely, the existence of lattices of packings in those dimensions that do that job. So you cannot beat this bound because there's a competing force that you just matched, In the other dimensions, these Fourier optimization problems give certainly upper bounds, but the best examples known from the other side do not match these upper bounds. They're still a little bit far away. So this suggests that maybe there is a different Fourier optimization problem that maybe could get closer to the answer, and that could be the correct one, still to be found, maybe. Anyway, a little bit of the history. Examples of Fourier analysis in number theory include the example I just described, but include sorts of Erdős-Turan discrepancy inequalities for sequences modulo 1, Hilbert type inequalities and large sieve inequalities in number theory, sphere packings that I just mentioned a little bit, this phenomenon of sign Fourier uncertainty that was introduced by Bourgain, Kahan, and Clauzel a few years back. Bounds for the Riemann zeta function on the critical line and on the critical strip. Bounds for Montgomery's pair correlation conjecture. Bounds for low-lying zeros and the vanishing of L functions, bounds for prime gaps, and so on. So there's a lot of examples, a lot of situations in analytic number theory where techniques from Fourier analysis can be useful. Okay, so now I want to give to you a couple of concrete examples tonight. And I hope these are sufficiently simple for everybody to understand. So the first problem is a problem that dates back to Vinogradov. And I'm just going to consider quadratic residues here. So for me, Q will be a prime, let Q be a prime, and let chi be the Legendre symbol modulo Q. So if you don't know what it is, or if you don't remember, let me just define to you. The chi of n is essentially 1 minus 1 or 0 if chi of n is 1 if n is a square modulo Q, if n is congruent to a square modulo Q. Chi of n is minus 1 if n is not a square, not congruent to any square modulo Q. And chi of n is 0 if n is a multiple of Q. So for example, if you take Q to be 5, the squares modulo 5 are either 1 or 4. 2 and 3, these congruence classes, are not squares modulo 5. There's no number whose, when you square it, is going to be congruent to 2 or 3 modulo 5. All right. So chi of 1, 1 is always a quadratic residue modulo Q because 1 is 1 square. So you start this sequence you start with sequence with always chi of 1 being 1. And the question is, let me define this quantity n chi, which is just the minimal guy, the minimal natural number n, such that chi of n is not 0 or 1. Okay? So I really want to know what is the first, if I start, let's say, my natural numbers, if I start with 1, what is the first quadratic non-residue modulo Q? Okay? In this example, when Q is 5, that I just described, this least quadratic non-residue would be 2. 1 is a residue, 2 is not a residue. So Vinogradov was the first one who gave bounds for this quantity. He proved that this number n chi, the least quadratic non-residue, was at most a power of Q to the 1 over 2 square root of E log square Q. This is unconditional. And Burgess improved this bound to the bound which is essentially the best known up to today, which is n chi is at most of order Q to the 1 over 4 square root of E plus epsilon for any epsilon. Now, there is a recent paper by Yunus Lamzouri, Lee, and Soundararajan that if under the generalized Riemann hypothesis, so if you assume the Riemann hypothesis for Dirichlet L functions, you can do much better. You can actually prove that the least quadratic non-residue n chi is at most log square Q for any prime, and asymptotically for Q very large, you can actually prove that n chi is at most 0.8 log square Q. This result of Lamzouri, Lee, and Soundararajan improved previous classical results coming back to Ankeny in 1952 and Bach in 1990. These conditional results. So I'm going to be interested in this talk about these conditional results in the asymptotic regime, right? I want to do a little bit better and show you how we can do a little bit better with respect to this last result here stated on the board, this 0.8. So I want to see what is really the limit of the methods that you can use for this problem. So here's an example. Here's a table where you see the first column has the primes, okay, and then you have here the natural numbers on the row, on the lines. And for each prime, you have, well, 1, it's in pink if it's a quadratic residue, and -1 if it's not a quadratic residue. So the problem is, given a prime, in that row, you want to find the first -1 For example, if you get the prime 23, 1 is a quadratic residue, 2 is a quadratic residue, 3 is a quadratic residue, 4 is, and 5 is the first quadratic non-residue. So the answer would be 5. And you see, for 47, again, the answer would be 5. So you are interested to know how far you can go just with quadratic residues. That's the first problem. The second problem is also a problem which is relatively simple to state. It's a problem about primes in arithmetic progressions. So the statement is the following. Let Q be a modulus, natural number, and A be an integer, which is co-prime with Q. Now, let P of A and Q be the least prime in the arithmetic progression of numbers congruent to A modulo Q. A classical theorem of Dirichlet says that if A and Q are co-prime, there are infinitely many primes which are congruent to A modulo Q. And we just want to find the smallest prime in this arithmetic progression, okay? That's what we want. Unconditionally, a classical result of Lineik proved that P of AQ is at most Q to the L. And one can take L to be 5.5 in this bound. This is a result of Heath-Brown in 1992. That was recently improved by 5.2. And again, this is the best that one can do unconditionally so far. If you assume the generalized Riemann hypothesis, in the same paper, Lamzouri, Lee, and Sandarajan showed that for Q bigger than 3, this first prime is actually at most phi of Q log Q squared, phi of Q log Q squared. And this improved the result of Bach and Sorensen in 1996. So there is a constant here in front, which is 1. And I would like to take a look at this bound in the asymptotic regime when Q is very large and try to do better. Okay. The third problem of our conversation today is a problem in Fourier analysis. So let me remind to you what the Fourier transform is and what sort of Fourier optimization problems I'm going to have in mind today. So for f, an integrable function, we define its Fourier transform by this. This is the normalization that I use. F hat of t is just the integral from minus infinity to infinity of e to the minus 2 pi I xt f of x dx. This is the classical Fourier transform with the minus 2 pi I in the exponent here. This is how I normalize it. All right. Let me take the following definition too. For a real valued function g, let me consider g plus the positive part of g. By this, I mean the maximum between g of x and 0. And g minus, it's the negative part of g. It's the maximum of minus g and 0. You see, but these functions g plus and g minus are both non-negative, okay? And the function g can be written as g plus minus g minus, okay? So I take the positive part and the negative part. And, here's my problem. Given a parameter a between 0 and infinity, I want you to find this constant, which I'm going to call constant c of a, which is defined as a sup. It's a supremum over functions f in a certain class that I'm called italic a, where you have a constant 2 pi divided by the L1 norm of f. These functions are on the real line, so you're going to divide by the L1 norm, and you're going to take the supremum of this thing here. The integral of the Fourier transform f hat of t against this exponential e to the pi t dt in the negative axis minus the integral in the positive axis of the negative part of the Fourier transform f hat minus t e to the pi t dt minus this parameter a, and then the integral from 0 to infinity of the positive part of the Fourier transform e to the pi t dt. Okay? So I want to take the maximum. I want to find the supremum of this, where the supremum is taken over this class of functions. The class italic A is functions f from R to C, which are integrable and such that the Fourier transform is real valued. Okay, I want my Fourier transform to be real valued in order that these integrals, are all real valued, and I can talk about the supremum of these things. Well, when you look at this problem, you can see, well, it looks very hard to actually pinpoint the answer, and I tell you, it is. But you can guess a little bit just about from the formulation, right? So note that these terms, by definition, the second and the third term, they are negative, right? Because I told you that this f hat minus and f hat plus, these are non-negative functions. So you are subtracting something, okay? So if you want to find the supremum, these terms here, the second and the third term, they hurt you. They are bad. This is the guy that could be big and positive to help you. So you want to make this as big as possible and these as small as possible. It doesn't mean that you want to make this term and this term zero. Well, you could, but this is not necessarily the best answer. Maybe it's a little bit better that these are a little bit small and negative, but this will be a better positive number, So you want really to see the balance that you want to make. And note also that you're multiplying by an exponential here. So e to the pi t is multiplying here, here, and here. So especially this mass that is negative, if you put a lot of mass when t is large, it's going to be multiplying a huge weight, e to the pi t, if t is large. So this is not in your best interest. So you really want to move a lot of the mass to the negative, a lot of the mass of the Fourier transform to the negative axis.
Sorry, Emmanuel.
Go
may
ahead.
I ask you, yes, I have some question. When you define this constant that depends on A, you divide by the L1 norm of the function, right? This is to have finite this quantity, or this is some normalizing factor? That
Yeah,
you
this
put
is
to
just
find?
well, it serves several purposes, right? But one is that you can just not dilate your function. Multiplying your function by 2 doesn't change these things, right?
Right.
So you really have to do
Okay.
some sort of normalization to avoid cheap tricks like this. So if I multiply f by 2, I multiply the Fourier transform by 2, but everything, the numerator and the denominator are multiplied by 2 and you cancel, okay? So really, the problem could be stated in a different way. Assume that the L1 norm is 1. What's the supremum of these things? Does that answer your question?
Yes, Emmanuel, thank you.
Okay. By the way, if anybody else has any question, feel free to jump in. Okay, so we have this, it's actually a family of problems, okay? For each parameter A, you have a family of problems. You have a problem. For each A, you have a problem. Note that when A is 1, for example, when A is 1, you get here on the right-hand side these two integrals, f hat minus and f hat plus, and you're adding them. When you add the negative part and the positive part, you get the modulus of the function, okay? I told you that before, that g was equal to g plus minus g minus, and modulus of g is equal to g plus plus g minus, okay? So this parameter 1 will be relevant. Okay, moving on. So, okay, just a little glimpse of the shape, So this is what intuition tells us, what the maximizer wants to be. So it wants to concentrate a lot of the mass on the negative side and maybe have just a little bit of mass on the positive side. If it has mass on the positive axis, it has to be very, very small because these are hurting you. Okay? So this is kind of what the extremizer would like to be. And the next question is, what do these three problems have in common? Then, well, these are kind of the two results that I would like to call your attention to. So with respect to the first situation, the situation of quadratic residues, so assume the generalized Riemann hypothesis, let Q be a natural number and chi be the Legendre symbol modulo Q, then, remember this n chi is the first quadratic non-residue. If you divide by log square q, the lim sup of this thing is at most this constant c of 1 to raise to the power minus 2. Okay, so this is an upper bound for this quantity. And you see the second theorem with respect to the primes in arithmetic progression. If you assume again the generalized Riemann hypothesis that q be a natural number and a an integer co-prime with q, then the least prime PAQ congruent to a modulo q verifies this bound. The lim sup, again, I'm looking at the asymptotic regime of PAQ divided by this quantity phi of q log q squared, is at most this constant c of 3 of our Fourier analysis problem raised to this power minus 2. Okay, so there is a first part in our framework, which is to connect the number theory problems to the Fourier analysis problems. So imagine that up to this moment, you don't know how to solve those Fourier analysis problems, but you can just prove an upper bound for a number theory problem with a Fourier analysis problem. And then you can say, well, and then you can give this Fourier analysis problem to an analyst, you know, can you please help me solve this problem or find an approximation for the solution? And then the person can just solve the analysis problem on its own, because I mean, it has no number theory at all, right? This is the step 2 in our framework. Once we have proved that these two things are related, now I would like to find an approximation for these numbers. And then it turns out that you can actually prove I cannot actually find the exact answer for C of 1 or C of 3. These are hard problems, but we can actually give very precise lower and upper bounds on what they are. For example, this number C1 to the minus 2 is between 0.7595 and 0.67615. So notice that the best known result before was 0.8. So I'm just showing to you a method that will give you something theoretical, but in practice, it's at most 0.76. So we are improving on the current best bound. Analogously, the second problem, the current best bound was 1, and we connected to a Fourier analysis problem whose answer is this, which in principle I don't know, and then we try to solve this problem and we find near extremizers. We study this constant and prove that it lies between two very, very close numbers, 0.885 and 0.889, 8 over 9. So we can give very precise bounds for this number. In particular, the previous best bound for this problem, which was 1, is now decreased to 8 over 9. So this is an improvement on the about 10%, almost, I mean, on the current best bound for this problem. Okay. So this is how these situations connect. And now I want to spend maybe the next minutes giving you an idea on how to connect these things. Let's see. Let me first talk a little bit about the analysis problems. You know, what can you say about that analysis problem? You know, and we can actually say a lot of things. And I just summarize here in this table some of these things that I can tell about the analysis problem on its own. You know, this is the interesting stuff that I find about these topics. You know, you have a number theory problem, you can isolate an analysis situation that you can give to an analyst to work on, and this person will be able to work on 100%, because this is really a problem that has no number theory at all. Remember that the problem was about finding the sharp constant in a certain class of functions. So I tell you the following propositions hold. The first thing is you can actually consider a restriction to Schwartz functions in that class. This is okay. The second thing is that this map that sends the number a to the constant c of a is continuous and non-increasing as a increases. The non-increasing part is easy because if you remember, a was on the penalty side. So the larger the a is, the lower the constant is. But it's interesting that the answer that in principle is just an infimum is actually continuous on the parameter a. We can actually find the sharp constants just in two cases, when a is 0 and when a is infinity. the two endpoints. So when A is 0, the answer for that problem is C of 0 is equal to 2. And when A is infinity, the answer of that problem, C infinity, is equal to 1. So you really go from 2 to 1, and everybody else is in the middle. So here are some values. We can prove very precise lower bounds and upper bounds for our problem. For example, C of 1 is between these two numbers, 1.146 and 1.147. C of 3 is between these two numbers, 1.06, 1.062. Now you look at these numbers and you say, well, how do you actually prove these things? You know, the upper bound is finding an example, finding a near extremizer. Remember that your problem is to find the infimum of something, right? So for any example that you plug in there, it has to be bigger than the infimum, right? So you have an upper bound. So you really have to put your programming skills to work with a certain basis of functions, let's say polynomials of degree up to 100 multiplied by certain functions. And then within that finite dimensional subspace, you can run the usual technology to try to find a near extremizer, you know. And as you raise your degree long enough, you get better and better approximations. So you really can produce examples that, let's say, this will give you upper bounds. The lower bounds are more interesting in a first moment. You know, how do you prove that an infimum is bigger than something? This requires some thought. This is just well, it's just a glimpse of some of the test function that appears, you know, in this. I'm sorry, I've been saying something wrong, right? I wanted the soup. My problem is to find the soup of something. So the lower bounds are given by example, and the upper bounds are the problem. So the lower bounds, this is a glimpse of some test functions that we want to use, right? So your problem is to find the soup of something. So any test function that I put here will give me a lower bound. So in particular, if you take this very clever function, which is an exponential multiplied by a polynomial, shifted a little bit to the right, you know, and then you play a little bit with the numerical side, with the coefficients of the polynomial and the shifts and the dilation, you get a suitable example, you know. And then we can play this game with polynomials of degree 7, 9, 11. In this case, the polynomial has to be an odd polynomial. So this is an example, actually the example to prove that C of 1, which is the number that we're interested in, is bigger than something. The upper bounds, they come from some sort of dual problem in analysis. You know, this Fourier optimization problem has a certain dual problem that I won't explain too much what it is here, but instead of looking for the supremum of something, is now finding the infimum of some other thing in a certain class. And you can actually, you know, prove a proposition like this, that the constant that we're looking for is bounded by this C star, and the C star is the infimum of something. So to get any upper bound for C star is just by putting an example in the dual problem. You just have to find a good example to plug in here, okay? And the same game repeats. You have to use your, you know, linear programming tools to approach this and try to find near extremizers. Now, maybe for the final part, I want to talk a little bit about what I find most interesting thing, which is actually to make this bridge that connects the number theory to the analysis. You know, how do you actually prove that theorem without knowing what this constant is? How do you prove that the number theory quantity is bounded by that constant? Okay, and this goes a little bit towards this, uses this so-called explicit formulas. You're working with the Riemann zeta function, or in more general with an L function, and there are formulas that relate the zeros of zeta with the prime numbers and the Fourier transform. I'm going to show you how they are obtained. So if you consider the Riemann zeta function as usual, sum of n to the minus s, first you define to the right of 1, and then you know that there is a way to extend this function to a metamorphic function on the plane, on the complex plane. If you define, for example, this xi function to be zeta multiplied by gamma of s over 2, pi to the minus s over 2, and then s minus 1, call this function xi, then the functional equation can be written in this form. There's a very nice functional equation that this function xi verifies, which is xi of s is xi of 1 minus s. And this is how you start with something defined to the right of 0, and you move and define it to the left of 0 as well. Okay, and this function xi has the same, non-trivial zeros of zeta. There are the trivial zeros of zeta, which are at the negative integers. These are killed by the poles of gamma. So the zeros of this function xi are exactly the non-trivial zeros of zeta, which are supposed to be, according to the Riemann hypothesis in this line, real part of s equals to 1/2. But they are, in principle, they are all inside the critical strip. Now, and then what you have to do is some sort of contour integration. So I'm telling you how you derive these explicit formulas. So you take h to be a good function, and I won't tell you what a good function is now, but let's say h is a certain good function, and you can imagine that you want to start with a contour integration on a square and then take the limits when the boundaries go to infinity and move the lines as well. So you need the function h to have some decay for you to do that. But first of all, you start with some contour integral in a rectangle like this, from minus epsilon to 1 plus epsilon at height t and minus t. And you integrate this function h, rho. I mean, you consider this integral, contour integral over the contour, 1 over 2 pi I, integral over this contour c of this function, h of s minus 1/2 over I, xi prime over xi ds. So you start with this contour integral, and the first thing that you know, by the residue theorem, this can be evaluated. This is just, the poles of this thing are just the zeros of xi of s, are the zeros of the zeta function, right? And so this will be evaluated at, assume that h has no poles. This will be just the sum of the residues of this function at the poles. And then, but this residue of xi prime over xi is 1, so this is going to be just h of rho minus 1/2 over I for every 0 of zeta. So the residue theorem tells you how to evaluate this integral directly as a sum of the function h over the zeros. And now what do you have to do? Well, now you have to take your expression for xi, written right here, and xi prime over xi is this log derivative of xi. So you have to decompose it. It will have the derivative of this, the derivative of this, the derivative of this, the derivative of this, and the derivative of this. It will have 5 terms. You open them up, and then you take your contour that has 2 symmetries. It has the functional equation that xi of s is equal to xi of 1 minus s, and also that this function is a real entire function. So the values on z and z bar, they are related, So you use these 2 symmetries to transform this rectangle into just 1/4 of it. And then you evaluate these pieces closer, each of these 5 pieces. At the end of the day, you're going to get a formula. I'm just going to show you what it is. You're going to get a formula that relates the test function at the zeros and some sum on the other side. And the same game that I just described to you here, how to play for the Riemann zeta function, you can play for a Dirichlet-Elf function. A Dirichlet-Elf function is just, let's say, the first generalization of the Riemann zeta function, where you consider the function n to the minus s multiplied by a certain character, chi of n. For example, the Legendre symbol, but you can take any multiplicative function, modulo q, and plug it in here. This is called the Elf function, ls associated to the character chi. The Riemann zeta function is a particular case just when chi of n is 1 for every natural number. But this function chi of n should be multiplicative. In the, well, chi So character modulo Q should be 0 on the multiples of Q and multiplicative in the reduced residues. Okay, so this is what you get. It looks ugly, and of course, I don't want you to memorize what it is. I just want for you to have a feeling of what it means, you know? So this is, let H be a function which is good, and good is, in this case, analytic in a certain strip containing the real axis and having some decay at infinity. H of S less than 1 plus S to the, let's say, minus 1 plus delta, as S goes to infinity. Let chi be a primitive Dirichlet character modulo Q. Then the sum over H over the ordinates of the zeros, of the non-trivial zeros of this L function, this is the left-hand side, is equal to a certain sum on the right-hand side here. This is what you get. H hat of 0 times log Q over pi over 2 pi, plus an integral involving H and the log derivative of the gamma function, plus some sum involving this von Mengelt function, lambda of n, square root of n, and then the character and the Fourier transform applied at the points log n over 2 pi and minus log n over 2 pi. So this is an identity. Why do we like it? Well, it has the zeros of my L function. It has the prime numbers because this von Mengelt function is essentially a function that captures the nature of the primes. So this is a function that is log p if n is a power of prime and 0 otherwise. So this captures the information about the prime numbers. And you also have the Fourier transform here, the Fourier transform of H evaluated at some points. So a formula like this has three things that we like. It has the zeros of zeta or the L functions, it has the prime numbers, and it has the Fourier transform. And you can plug in this formula any function h, which is relatively good, any test function h that is relatively good. So what do you do when you want to investigate a number theory situation that has something to do with this formula? Well, you look at this formula for a long enough time, trying to think about how you would particularly set up or choose your function h in order to extract from the formula the information that you want. This is essentially the philosophy. And let's try to do, let me show you broadly and vaguely, because this involves a certain non-trivial number of technicalities, how to do this in our situation. Let's go back to the situation of the quadratic residues. Assume that Q is a prime and chi is the Legendre symbol. Let me set up this parameter delta to be, remember that I want to find a bound for this n chi. I want to show that this n chi is log square. So we're talking about log Q morally. So this delta is log n chi over 2 pi. And then I'm going to take a function f in my class A that I defined there in the beginning. Remember, this class A was just integrable functions such that the Fourier transform was real valued. And I'm actually going to take Fourier transform real valued and smooth and compactly supported, because I told you that I could take a function to be Schwartz if I wanted. And the answer of the extremal problem was going to be the same. So fix a Schwartz function with the Fourier transform compactly supported in your class. Fix this f and set this function h hat to be used in your explicit formula to be this. F hat of t minus delta plus f hat of minus t minus delta over 2. This is an even function. This h hat is an even function. So you take this and you plug into that formula. So the explicit formula yields, when you plug in this function there, it yields this thing. Here's the sum of h over the ordinates gamma chi, or the ordinates of the non-trivial zeros of this L function, and you are assuming the Riemann hypothesis, so all these non-trivial zeros are 1/2 plus I, this gamma chi, plus the other terms, h hat of 0, some integral involving h and the gamma function, and the sum over primes, which now, because h is even, it simplifies to just these things. So this is what the explicit formula gives you. And I have, remember, this is an equality. I have already singled out the blue terms, because what you want to generate when your parameter delta goes to infinity This is what you want. You want to send delta to infinity at the end, right? You want to generate a competition between some of the terms in the explicit formula. So these two blue terms are the terms that will compete, and the terms in black will be error terms, okay? So let me analyze these two blue terms here. The idea is to proceed with an asymptotic analysis of each of these terms, and I'm already telling you which terms are going to compete. Well, the right-hand side, this term here, it's a sum. So this is interesting. This is really, this was just a sum from n to infinity of this quantity. Lambda of n, remember, this is a function which was log p if n was a power of p. The character chi of n divided by square root of n, and then h hat at this point. This is the moment where you want to use the information that you have, okay? So all the information that you have is that this character chi of n is 1 up to this number n chi. And from that number on, you have the first -1, and then you don't know what happens, right? So I'm going to break the sum that went from 2 to infinity. I'm going to break exactly at n chi -1, and then from n chi to infinity. I'm going to break it into two parts. I didn't do much. But what happens is that this first part, I know exactly what n chi is. N chi from 2 to this, sorry, chi of n from 2 to this number n chi is 1. Because the first quadratic non-residue is this number n chi by definition. So this is 1. This, I cannot do much. I mean, this could be -1 all the time. So I just bound this. I just put bigger or equal than, and I just take the modulus of everything. So the modulus of chi of n is always 1 or 0. And then you take the modulus of h hat. And this term in red here is just an error term that appears because, technically speaking, the chi of n is 0 at the multiples of q. So you have to sum these guys and subtract. And this is what you get as an error term. Anyway, so this is just to say that the error term is small. And then you get these two sums. So a sum from 2 to a certain number and a sum from n chi to infinity. You see there is no character chi anymore here. And there are ways that you can transform these sums in number theory into integrals using the so-called prime number theorem or an integration by parts. So you can actually use integration by parts or summation by parts, if you prefer, to say that this sum is morally this integral here, and this sum is morally this integral here. You see a modulus of h hat will become a modulus of f hat, plus an error term, okay? And again, this passage asterisk uses this sort of version of the prime number theorem, that you know what the partial sums of this von Mangold function lambda of n are up to x. This is x plus an error term. So if you know the partial sums of one thing, you're going to use integration by parts in this formula. Bottom line is you have written your right-hand side as some integral plus an error term, some integral that depends on delta. You're going to do the same with the left-hand side. Again, the left-hand side is we're going to bound it above by the modulus of the sum of h at the ordinates, which is, you know, just the real part of, I mean, you use the definition of h right here. And so h of somebody is the real part of this f modulated by this exponential. And you move the modulus inside, loses to the sum of the modulus of f. And again, you use some sort of integration by parts here with you're summing a function f over all zeros. So you're going to use integration by parts with this zero counting function n of t. And you have very explicit expression for the zero counting function, the function that counts the zeros up to height t. And integration by parts is going to lead you to this sort of main term plus this error term, okay? Again, this uses that the function that counts the 0 up to height t is essentially equal to, this is the main term and this is the error term. At the end of the day, when you put your pieces together, you know, we had something in the explicit formula that was originally an equality. What we did was we took the left-hand side and we put an upper bound for it. We took the right-hand side and we put a lower bound for it, and we had some error terms. So all you have at the end, if you put the pieces together, is an inequality. This thing that you got from the right-hand side is less than this thing plus an error term. And when you recall that this parameter delta was given in the beginning, right? So this n chi is e to the 2 pi delta. So this is actually square root of n chi, square root of n chi. When you divide by log q, so you get square root of n chi divided by log q, and you move everything else to the other side, you get that this is less than, well, when you divide things by log q, this error term will disappear in the lim sup, right? So you get that the lim sup of square root of n chi log q as you wanted, it loses to this number here. Remember, everything that I did now had an f fixed in the beginning, right? So you fix an f, Schwartz, and you get this inequality. At the end of the day, now the left-hand side is just a number, which is fixed and doesn't depend on your f. This is a number that exists in nature, and it's there. Now, the right-hand side depends on f. Now, what you can do is you take this right-hand side and you optimize in f, because for any f that you put here, you're going to get an upper bound for this quantity that you want. So you might as well put the infimum over the right-hand side here over f, which is essentially our problem was just the reverse of this thing, right? So now if you optimize the right-hand side, you get exactly the original problem inverted, c of 1 to the minus 1. And then you get c of 1 to the minus 2 because you have to square everything. The original quantity was not square root of n chi over log q, but n chi over log q squared. And this is how you get c of 1 to the minus 2 as your upper bound, okay? So this is just I know it's a bit fast doing this thing, but I wanted just to pass the moral message is that you start with some sort of explicit formula that involves the ingredients that you have, the prime numbers, the Fourier transform, and the zeros, and you have a certain number theoretical situation. In this case, that my quadratic residues are 1 up to a certain point, and then the first minus 1 appears, and you want to somehow use that information in the explicit formula with a suitable test function. And this is, well, this is the hard part. You have to think about for weeks and weeks and weeks how to do this properly. But if you manage to do it right, some nice Fourier optimization problem here appears on the right-hand side, and this is what you are led to. The other problem with primes in arithmetic progression follows the same philosophy. It has its own technicalities and its own way of doing this thing, but the moral is, the philosophy is the same, but I won't have time to discuss today. All of these things, we're finishing a paper on this thing. Is not exactly on the archive now, but it will be, I hope, in a month or two, okay? Thank you for the attention.
Hey, Emmanuel, thank you very much for this very nice talk. So, are there any questions for Emmanuel?
In the chat, Ruben.
In the chat, Okay, so someone, John asked briefly, what is the history behind the definition of C of A? He asked.
Well, that's a good question. You know, when we wanted to analyze the situation for these quadratic residues, we found this optimization problem. When we wanted to analyze the situation for the primes, we found a different Fourier optimization problem, but which was very much close to this one. And there is everything that I told you today is part of a bigger result, which is to actually take a character instead of the quadratic character. You can take a character of a certain given order, right? If a quadratic character is a multiplicative function modulo q in the class of residues modulo q that has just values 1 and minus 1. But a cubic character will be a function that has values, the third roots of unities. It's a function that when you cube it, chi-cube is identity. A quartic character, so the order, if a character has order L, if I take this character and raise to the L power, then it's the identity, right? So you can ask the same question, you know, you can ask, what is the first known residue? What is the first guy in the sequence that is not 1 for that character of order L? And this is kind of related to the same Fourier optimization problem, but with parameter 1 over L minus 1. So remember, when L is 2, we're talking about quadratic characters. I got C of 1. But in general, for order L, I will get C of 1 over L minus 1. So this is why the proposition I had in the beginning had some values like 1/2 and 1/3 as well, because this could be used to other problems in number theory. And at the end of the day, you know, thinking as an analyst, it was just easier to put all of these Fourier optimization problems in a family with one parameter that we just call A to make the analysis simpler and I think in my taste, you know, more neat, you know, more clean, you know. So just consider this family. So this is how these problems appear.
Very good. So, Emmanuel, I have a question about myself. In this inequality that you show here, my question is if you can find one sequence of primes that converge in such a way that this when you take this limit converge to the right-hand side of the inequality, or if in the opposite you can take one sequence of function that converge reaching the lower bound. Is that possible, or you have some gap between these two quantities?
No, that's a very good question, Duvan, also. But I think for these problems and for other similar problems in number theory, this thing might not be the same. This thing might not be the correct order of magnitude. So I'm studying to you this inequality here, right? I'm improving on this inequality here, that n chi is less than 0.76 log square cube. But I think it's kind of conjecture that the true order of magnitude should not be log square, should be maybe log to the 1 plus epsilon, okay? So, but this is a much harder problem to actually improve on this exponent 2 here. So far we can't do it. What we can do is improve on the constant in front. But, you know, so the short answer to your question is no, there is still some gap. So in principle, there could be a better Fourier optimization problem that would actually improve on this order of magnitude, but we don't know how to do this.
Thank you very much, Emmanuel. So are there any more questions for Emmanuel? So if not, then Emmanuel, thank you very much for your talk and for supporting our project.
Thank you all. I think it's a lovely project. Happy to be here. And I thank everyone who was here with us today.
Thank you, Professor Emmanuel. Hello, everyone. Welcome to the last talk of this conference. For this talk, we have José Luis Ramírez as host. He works at Universidad Nacional de Colombia, and he is member of the scientific board of this conference. Whenever you want, you can start, José Luis.
Thank you, Yuriko. Hi, everyone. Today I have the pleasure and honor to introduce the last speaker in this conference. She is the Professor Pamela Harris. Dr. Harris is an associate professor in the Department of Mathematical Sciences at the University of Wisconsin at Milwaukee. The main topic of research of the Dr. Harris is algebraic and enumerative combinatorics. In particular, Dr. Harris is interested in the problems about representation theory of the algebras. I have to say that Dr. Harris is also interested in several discrete objects like parking functions, set partitions of type E, B, etc., permutation, graphs. Very interesting results about the combinatorics behind of these objects. Dr. Harris is also co-founder of the Latinos and Hispanics in the mathematical science. And in general, I would like to say that if you are undergraduate or graduate student interested in combinatorics, please visit the webpage of Pamela, because you can find very interesting information about mathematics and about the Hispanic community in the United States. Thank you, Pamela. And today, Dr. Harris will talk, finding needless in high-stack Boolean intervals in the weak order of the symmetry group.
Thank you so much, Jose. It's so great to see you again. So I'm super excited to be here today, and I want to share with you the story of a project that we undertook. And when I say we, I like to lead with the folks that helped do all of this work. So Jennifer Elder, she's an assistant professor of mathematics at Missouri Western State University. Jan Kreshman, who is one of our wonderful PhD students here at the University of Wisconsin-Milwaukee. Juan Carlos Martinez Mori, he is a Schmidt Fellow and has an appointment at the Mathematical Institute, who used to be MSRI and now is SL Math, so in Berkeley, California, but he's also a postdoctoral fellow at Georgia Tech. So these are the people behind all of the really cool math that I'll show you today. And so the title of the talk is Finding Needles in Haystacks. So that's the first part of it. And, I'm originally from Mexico, and I came to the States, and there's all these sayings in English that I sometimes don't understand what they mean, so I have to look them up. But I looked this one up, and it felt really close to what it is that I'm going to show you mathematically. So this just refers to having something really difficult to do and finding some objects. And so if you imagine that you have just a giant amount of hay, and I throw in a needle in there, you can imagine how difficult it would be to try to sort through the hay to try to find that needle. And that's the reason why we call this, because here's the picture that I want to show you so that you see the kinds of objects that are going to be the haystack and the kind of objects that are going to be the needles. So here's the picture that, should be plastered somewhere in my mind, at least it is. So I have this giant poset, and we'll go through all of the definitions because I like to not assume anything of my audience. So here's this giant poset, and then what a needle would be in this case is maybe this little B3, and I'll define what I mean by a B3, but just this little cube sitting inside of there. And so let's think a little bit about the big object, so the haystack. So the first thing I need to define is a poset. So when I talk about a poset, I'm just thinking about a partially ordered set. So a set, and I have some relation on the objects so I can compare them. And it has to satisfy some properties. So the first property is reflexivity. So that means that if I pick A out of my set and I try to compare it to itself, I could say that A is less than or equal to itself. I also have the property of anti-symmetry. So if I pick two different elements, if I have that A is less than or equal to B and B is less than or equal to A, then it must be that in fact they're equal to each other. And then transitivity. So if I have three different elements, A, B, and C, okay, not necessarily different, but I have three elements, A, B, and C, and they satisfy the conditions that A is less than or equal to B is less than or equal to C, then it must be that A is less than or equal to C. So now let's just recall some things about posets. So we talk about a poset being ranked if I can put a function on the poset that takes me from elements of the poset to some non-negative integer. And I just need to ensure that it satisfies the cover relations. So what I mean by that is that if I know that X is less than Y inside of this poset, then that must mean that R of X, whatever value I assigned using this rank function, must respect the fact that it's less than R of Y. And also, if Y covers X, meaning nothing is in between them, then it has to be that the value I assign to Y using this function R must just be one more than what I assigned to X. So as long as I can create a function that does this, then we refer to our poset as being ranked. Okay, so let's think a little bit about then the needles that we're going to look at. So I'm going to look at Boolean posets, and the way that these are constructed is I just have some set that's ordered by inclusion. And so here's the empty set. So I would denote that poset, the Hasse diagram for it, just as a single dot. And then I might have a one element set. Okay, well, the subsets are the empty set and the one element set itself. And so I would connect those, and that would be my B1. So again, the containment here is what's allowing me to draw this little edge. But maybe I have a two element set. So the subsets, the empty set, which is a subset of this one here, the set with the one, or the set with the two, and then both of those are contained in the set with 1, 2. And then here's the B3. So you can follow the containments. And then again, you know, there's these nice little pictures that get associated to these. Now, this is a ranked poset, and the way that we think about the function is just the size of the set. So here at the bottom is all the elements that the rank function would assign a 0 to. Here at this kind of first level, it would be all the elements that get assigned a value 1, above that value 2, above that value 3. All right, so let's go back to our little haystack. So now that we know the notation, you can see that there's this B3 sitting inside of there. Okay, so there's that B3 sitting inside of this haystack. But let's go back and think more about this haystack. So what I'm going to do is I'm going to denote by this frac S the symmetric group. And I'm going to think about simple adjacent transpositions. So these I'm going to denote with an SI. And those are just the transpositions that swap I and I plus 1. Now, what I'm going to do is I'm going to define the weak right Bruja order, which we denote with a WSN. And I'm going to tell you how that is a poset. Now, of course, for those of you that know all this stuff, and this is just a summary of things that you're well versed in, of course, we could also do the left, but everything that we'll do today is going to be on the right-hand side. Okay, so to define the poset, I need to tell you how I'm going to decide whether one permutation is smaller than the other. And so I need to think about the cover relations. And the way that we're going to define that is by applying this simple adjacent transposition on the right-hand side. So this is where the right is coming from. Okay, so then I'm going to say that tau covers sigma if and only if I can write tau with a new SI on the right-hand side, and I actually get sigma. Now, the SIs that you're going to be able to use is going to be the ones that come from the descent set of sigma. So again, we're going to have a cover relation, so tau less than sigma, if and only if I can write sigma as tau times SI, where the I is coming from the descent set. And we recall that the descent set is a set of indices at which the permutation has a value that comes down. Okay, so in general, what's going to happen is a tau is going to be less than or equal to a sigma if I can have some collection of SIs that I put on the right-hand side of tau and I recover sigma. Okay, so that's how we're going to have this poset. Excellent. So let's just actually do an example, because again, I'm not assuming that you might have seen this before. And so let's go ahead and look at what I claim are cover relations in the weak order of S4. Now, I'm writing all of my permutations in one-line notation, and very quickly you will see how I'm going to just abuse notation. Okay, so I claim that this tau element, so this permutation 2, 3, 1, 4, is covered by two permutations, this 3, 2, 1, 4, and this 2, 3, 4, 1. So let's try to decide, why is this true? Why does 2, 3, 4, 1 cover 2, 3, 1, 4? So the first thing I need to do is I need to come up with the descent set for that permutation. And so if you notice, again, I'm going to find the indices at which the value went down. So here I increase some more, but now I decrease. So that was at position 3. So then the descent set for that permutation is 3. Now the cover relation says that if I can write tau times S3 and I recover 2, 3, 4, 1, then this is in fact a cover relation. So here's where I'll abuse notation a little bit. And I'm going to put just brackets around my one-line notation for tau. And I'm going to put my S3 on the right-hand side. Now remember that that's just going to swap the values that I see at index 3 and index 4 in the permutation tau. So if I do exactly that, it does in fact take those values and give me back this sigma here. So this 2, 3, 4, 1. So that means that we do have a cover relation. So 2, 3, 4, 1 covers 2, 3, 1, 4 through the action of S3. All right, let's do one more just to get our hands a little bit dirtier. So again, let's check this cover relation. So 3, 2, 1, 4. I compute the descent set. So in this case, notice that immediately I came down. So I throw a 1 in my descent set. And then I came down again. So there's a 2 in my descent set. And then I went up. So that's it. The descent set for that permutation is 1, 2. And now the question is, well, what do I need to apply to tau on the right, an S1 or an S2, to end up getting to 3, 2, 1, 4? And if you swap using S1, you end up seeing this cover relation. Now, of course, this does tell me that 3, 2, 1, 4 actually covers something else off on the side, but we'll see that in a little bit later. Okay, and then of course you can check then using the same kind of computation that 3, 2, 4, 1 actually covers both this 3, 2, 1, 4 and the 2, 3, 4, 1. So that one was by S1. And then here's the full cover relations and what element you applied on the right to get to that cover. Okay, great. So now some more definitions. So recall that a poset in which every pair of elements has both a least upper bound and a greatest lower bound, that's what we call a lattice. And we also say that a lattice is bounded if it has both a greatest and a least element. Some notes for us to take away from this is that the weak order of Sn is in fact a bounded lattice anytime that n is bigger than or equal to 2. And in one-line notation, I can quickly pick out the minimal element. This is the element that's just 1, 2, 3, 4 all the way to n. And the maximal element is the reverse of that. So n minus 1 all the way down to 2, 1. So let's look at the weak order of S4. So if you notice, here's my minimal element. Up at the top is my maximal element. And I highlighted here the B2 that we were just playing with. So the one that we checked all those cover relations for is highlighted here, slightly thicker edges. Now, one claim that I'll make is that if you take some time and just look at this, you can find 6 different copies of this little square sitting inside of this poset. And we'll check that in a while with a formula, but there's 6 of them. All right, so let's now have this question to think about. So suppose that I pick some minimal element and some maximal element. And then the question that I ask is, when is everything lying in between something that looks like a Boolean poset? Or can I even find something in between that has those shapes? And so what we're going to do is we're going to think about Boolean intervals in the weak order. So here's a definition of an interval. So I take a subset, and our notation is minimal element sigma, maximal element tau. So that's a subset of the weak order of Sn. And that's going to be an interval that contains everything in between. So sigma is less than or equal to tau. And anytime that pi lies between those two, then we're going to include it in this notation. So in this interval. All right. Now I'm going to get to add the word Boolean to in an interval. A Boolean poset appearing as an interval in the weak order is what we call a Boolean interval. So if it has that form that we were seeing before, like the B0, B1, B2, and so on, and it happens to be an interval, then we call them Boolean intervals. Now, Bridget Tenner has some really awesome results related to the Boolean intervals inside of the Bruja order and the weak orders. So the first one that I'll point out, oh, and if you want to read more, here's a citation. But two that'll be helpful for us is this corollary 4.4 in her article that says that Boolean posets appear as intervals with minimal element V, maximal element W in the weak order of Sn, if and only if, when you do this computation, B inverse W, that is a permutation that is composed of only commuting generators. So it's a product of SIs where you can move them in any order that you want. So that's one of the results that appears in that article. Another is this proposition where you fix I, some value between 1 and n minus 1. And then the claim is that the number of Boolean intervals that have the form, again, an interval, starting with minimal element Si, maximal element sum W, is actually given by a product of two Fibonacci numbers. Okay, so again, she fixed the minimal element Si and then said, okay, consider whatever W above it you want. How many Boolean intervals will we see of that form? And the answer is a product of two Fibonacci numbers. So as we were working on this, one of the research questions we were thinking about is, well, what happens if you have some other minimal element? What if it's not S1 or 2 or Si? What if you just have some other thing and now you have some arbitrary maximal element? In that case, how many Boolean intervals are there? So again, how many Boolean intervals are there where I fix some minimal element and then I let W be arbitrary above that? And I'm just going to spill the beans. Here's the theorem. The theorem says the following. So in fact, it is always a product of Fibonacci numbers. It might just not be two of them. And so this looks very technical, and we're going to break it down into pieces, but here's how it goes. So you tell me what you want to be the minimal element. This is this permutation pi. So that's going to sit at the bottom of the Boolean interval we're looking for. And then what I'm going to do is I'm going to look at the ascent set. So in contrast, before we were looking at the descent set because we were looking at things that were covering. Now we're going to see what is being covered above. So I look at the ascent set. And then what you do is once you know the ascent set of that permutation, you partition that set into the largest blocks you can that consist only of consecutive entries. Then, once you have those maximal blocks consisting only of consecutive entries, the number of Boolean intervals you can make, whose minimal element is pi, with arbitrary maximal element W, and here including the case where they're equal, is actually the product of Fibonacci numbers. Which Fibonacci numbers? Well, it is the size of those maximal blocks consisting of only consecutive numbers, adding 2 to that. So the index is the size of the block plus 2, and you take the product over all the blocks. And to index correctly, you start with F1, F2 being equal, both being 1. So this is the result that we were able to prove. Now, you might wonder, how did you arrive at this result? Okay, so this is where I now turn back time and I think about last summer. So last summer, Jennifer, Carlos, and I spent some time working at ICERM. So we ran this program called Computational Combinatorics. And we were working on projects that were related to parking functions. And so what I need to do to tell you how we proved all of this is I actually need to take you on a detour, puns completely intended, to the scenic route of parking functions. So I also wanted to point out that AIs are pretty incredible. So I generated this image from a prompt that said cars parked along a street, and then this beautiful image was created. So let's go down and study some parking functions. So here's how the game goes. So I have a street. It's a one-way street, and it has n parking spots, which are numbered 1 through n. Now what I'm going to do is I'm going to have a queue of cars. Each of them is going to enter one at a time, and they have their preferred parking spot. The parking rule is as follows. A car enters and always attempts to park in its preference. Of course, it might be occupied. Okay, if it's not, you park there, of course. But if it's occupied, then you continue down the street, parking in the very next available spot. So then the question becomes, if I give you the sequence of the car's parking preferences, do all the cars park? And if the answer is yes, all the cars park, then we call that preference list, or that sequence of preferences, a parking function. All right, so again, let's get our hands dirty, because I don't assume you've seen this before. So let's think about the tuple 1, 1, 3. So this is the sequence of preferences for car 1, 2, and 3 in that order. So car 1 prefers spot 1, car 2 prefers spot 1, car 3 prefers spot 3. So car 1 enters the street. It always gets what it wants. Car 2 enters the street wanting parking spot number 1, but it is currently occupied by car 1. So it'll continue down the street and park in spot 2. Car 3 enters the street, goes to its preferred spot number 3, which happens to be open, and so it parks there. And so in fact, this is a parking function. But let's look at what goes wrong if I change the parking preference for car 1. So in this instance, car 1 wants spot 3. It takes it. Car 2 wants spot 1. It takes that. Car 3 comes in and wants spot 3, but car 1 is parked there. So it is unable to park. That means that 3, 1, 3 is not a parking function. All right, so of course, we can look at tuples that are much, much longer, and trying to figure out whether they are parking functions or not. Well, it's not optimal to just draw the little lines and actually go through the process to see how the cars park. So there's a better way to test whether a tuple or a preference list is in fact a parking function. And that's this result. So if I give you a parking preference, let's suppose that it is A1 through AN, then what I do is I go ahead and I look at the non-decreasing rearrangement of that tuple. So I write the values in weakly increasing order. Then all I need to do is check if this rearrangement satisfies the condition that BI is less than or equal to I for every I. If that is true, then what you started with is a parking function. And in fact, this does a lot for us. It tells me that if I have a parking function, I can rearrange the entries in whatever way I want and return again a parking function. So this tells me something about the fact that parking functions are what we call permutation invariant. So you can permute the entries in any which way, and they'll still be parking functions. So let's go ahead and use this result real quick just to test those two tuples at the top. So what I did here is I look at this tuple, and then I write it in non-decreasing order. On the right-hand side, I just write the numbers 1 through 7. And then I check, are all those inequalities satisfied? The answer is yes. So in fact, I have a parking function. But if I look at the other one, notice that right away, no car actually prefers the first parking spot. So you're going to run into problems because you're going to have too many cars wanting too few spots. They're not going to be able to park. And so in this case, we don't have a parking function. So of course, one might wonder, if I tell you how many cars I have, which is equal to the number of parking spots on the street, how many parking functions are there? And there's this really wonderful proof by Pollock, who shows that if you park them on a circle, you do some modular arithmetic and some fun algebra, all of a sudden you end up getting that the number of parking functions of length n is n plus 1 raised to the n minus 1. Now, I got to tell you, I consider myself smart, but there's times I read stuff and I'm always like, there could have been much more exposition to this. And so I still think that proof is kind of hard to parse through on first attempt. And so one of the things that I'm very passionate about is making sure to also make math as accessible as possible. And with my PhD student who I co-advise with Steve Butler, so Kimberly Hadaway, who's at Iowa State University, I tasked her with making sure that anybody, you know, like a middle school kid could figure out how that proof went. And so she did just that. And there's 2 articles that got published in what is called Girls Angle Bulletin. And so I highly encourage you, especially if you're a researcher, to think about how you might be able to write some accessible part to describe the research that you're doing so that we can, you know, inspire a new generation of mathematicians. And so check those out if you're interested. Now, as Kimberly was working on those, she was giving talks about that work that she was doing. And here's where there was a really great idea that must be credited to Dr. Shanice Walker. So she's an assistant professor at Clark Atlanta University. And as Kimberly was talking about parking functions, Dr. Walker said, well, what if the cars can only park in their preference or in the very next spot? Like, they don't want to keep going down the street. They really only want to park in those 2 places. And so this led us to define what are now known as unit interval parking functions. And that is a subset of parking functions in which precisely that happens. So the cars either park at their preferred spot or at most 1 spot away. So for example, if I look at 1, 2, 3, 4, 5, well, that's a unit interval parking function. And the outcome, that's just another word for me to say the way in which the cars park, once I look at where they landed on the street, is actually the permutation. Car 1 takes spot 1, car 2, 2, car 3, spot 3, and so on. So 1, 2, 3, 4, 5. Let's look at this other tuple. So 5, 1, 1, 4, 3. And my goal is to determine whether that is a unit interval parking function, and if so, what the outcome is. So the first thing I'm going to do is claim that it is, and we're going to do a check. Okay, so here's my parking spots, 1, 2, 3, 4, 5. So car 1 comes in, and it wants spot 5. Of course, it's empty because nobody has come in yet. So car 1 takes spot 5. Car 2 comes in and wants spot 1. Well, that one's empty, so it takes it. Car 3 comes in, and it does want spot 1, which car 2 occupied, but it can park 1 away from its preference, taking parking spot 2. Car 4 comes in, it wants spot 4, that's currently available, so it takes it. And now we have this 5th car wanting the 3rd spot, which is also available, so it takes it. So now the parking outcome, I'm just going to drop the parking spot numbers at the bottom. So I get 2, 3, 5, 4, 1. All right, let's look at the tuple that consists of all the 1s. That is, in fact, a parking function. All the cars would be able to park under the classical parking rule, but it is not a unit interval parking function because the 3rd car would end up parking in spot 3, which is 2 away from its preference. Now, a really cool thing happened. When Kimberly was looking at this unit interval parking functions, which we're going to denote the set of with a UPFN, she noticed that, in fact, they seem to be enumerated by the Fubini numbers. And so the Fubini numbers, also people call them the ordered Bell numbers, so whichever you prefer, have this beautiful formula involving the Stirling numbers of the 2nd kind. And so once you get this, you start thinking, okay, what else is counted by Fubini numbers? Because either you can give a direct proof that this is the formula, or maybe you can biject onto another set of objects, which are enumerated by the Fubini numbers. And so this result came about from doing exactly just that. So the way that we prove that result is by giving a bijection to a set of objects, which we labeled Fubini rankings. I guess they're also called weak orders of the numbers 1 through n. We like Fubini because you'll see that you can define them as the competitions. So the way in which competitors can rank if you allow ties. And so we like the word rankings for that, and then Fubini because they're enumerated by Fubini numbers. Okay, so the thing that I should say is that Kaylee showed that those sets of objects are enumerated by the Fubini number, so we were able to rely on that enumeration, which we got for free after our bijection. All right, so Fubini rankings, like I said, so I'm going to have a tuple with n entries, and that's just going to record valid rankings of n competitors when I allow them to be able to tie. So many people can get first place, but there's a little caveat here. So if you do allow that, say, k competitors tie for some rank, say the ith rank, then you just need to make sure that the k minus for subsequent ranks are actually not appearing in your tuple. So what I mean by that is, for example, if you have 3 competitors, 2 people can tie for first, but then that means that the next available rank is the 3rd place position. So again, don't assume that you've seen these before. So let's just get our hands dirty and try to figure out which of the following are actually Fubini rankings. So here's the first one. So 1, 1, 3, 3, 5. So what does this mean? Competitor 1 and 2 tied for first place. So that disallows rank 2. But now the 3rd competitor and the 4th competitor tied for 3rd, which is totally fine. But now the 5th competitor could possibly get nothing other than the 5th rank. And so this is totally fine. This will be a Fubini ranking. All right, well now, if everybody gets a different rank, we're good. There's no ties, there's no problem. Everybody ties for first place. That's absolutely okay. Everybody wins the prize that day. All right, let's look at this one. 3, 1, 5, 1, 3. So in this case, competitor 2 and 4 tie for first place. Great, there's no 2s showing up. The next one is a 3, at which there's a tie. There's no 4s showing up. And then the next one is a 5. And if you notice, this tuple here is the exact same tuple, just rearranged from the first one. So this is also giving me some information about the fact that Fubini rankings are also permutation invariant. Okay, and here's this last one. And if you notice, it is not a Fubini ranking because competitor 2 and 4 tie for first place, but somehow competitor 5 got second place, which is not allowed under the Fubini ranking rule. All right, now let's go back and think a little bit about the difference between these sets. So we did give this bijection between Fubini rankings and unit interval parking functions, but look at what happens. So if I take the tuple 1, 1, 2, that is a unit interval parking function. Car 1 parks in spot 1, car 2 parks in spot 2, which is 1 away from its preference. Car 2 parks in spot 3, which is 1 away from its preference. But it is not a Fubini ranking, again, because the tie for first place disallows the second rank. Okay, so we can have something that's a unit interval parking function, but not a Fubini ranking. On the other hand, we could have something that is a Fubini ranking, but not a unit interval parking function. So in the example here, everybody tied for first place. That's totally fine under Fubini ranking, but not okay under unit interval parking function, because again, the 3rd car ends up parking in spot 3, which is not at most 1 from its preference. Let's look at the example 1, 1, 3. In this case, we kind of hit the jackpot. You're both a Fubini ranking and a unit interval parking function. So that intersection can be kind of fun. So let's look at the Fubini rankings. I'm going to denote those by FR of n. And then I'm going to just give you some information that we've uncovered through these examples. So first off, although these sets are in bijection, they're very different. So Fubini rankings are invariant under the action of the permutation group, but unit interval parking functions are not. The order is extremely important. You might permute something, and all of a sudden it is no longer a unit interval parking function. So an example to think about is 1, 1, 2. That allows the cars to park at most 1 away from their preference. But if I permute the entries and write them as 1, 2, 1, it is no longer a unit interval parking function because the 3rd car ends up parking in the 3rd spot, which is 2 away from its preference. Now, what I'm going to do is I'm going to look at the intersection of these two sets. And I'm going to call that unit interval parking functions. No, unit Fubini ranking, sorry. So I take unit interval parking functions, intersect with Fubini rankings, and then we just throw in the word unit in front of the rankings. So just a set at the intersection. And one way to think about this is that these are Fubini rankings where at most 2 competitors tie for any one particular rank. The really cool thing about this is that if you look at those that are weakly increasing, those are enumerated by the n plus first Fibonacci number. So now you're starting to see Fibonacci numbers come up, which remember were part of the big idea in counting Boolean intervals in the weak order. Now, not only that, we're able to count the number of unit Fubini rankings that have n minus k distinct ranks. And so we have this nice formula involving a binomial and a power of 2. So again, n minus k distinct ranks, which means that there's some ties happening here. Now, what's the big idea? Okay, so I took you down this, rabbit hole to go explore parking functions, and then Fubini rankings, and then we looked at the intersection between Fubini rankings and unit interval. But here's the big idea. The big idea is that what we were able to do is connect unit Fubini rankings precisely with Boolean intervals in the weak order of the symmetric group. And the way we did that is by showing that, in fact, those two sets are in bijection. And not only are they in bijection, but the ranks, or the number of distinct ranks in the Fubini and the rank of the Booleans, match up in some way. And the way they match up is I look at Fubini rankings with n minus k distinct ranks, and that set is in bijection with Boolean intervals in the weak order of rank k, which is great because then we can use the enumeration that we had for Fubini rankings with n minus k distinct ranks, and then it directly applies to the number of Boolean intervals of a given rank. And so in that case, it gives me the exact same formula. Now, let's go back to the example that we had at the beginning. Remember, I claimed that there were 6 copies of B2 in the weak order of S4. So what I can do is I can use the theorem that I just showed you. And, I did the algebra in advance. And in fact, you do end up getting 6. And I highlighted them for you. So there's a blue one at the bottom. There's a red one or orange. There's a blue, there's a green, and there's a pink up at the top. And the black that we had already confirmed. So that gives us the total of 6 different B2s living inside of the weak order of S4. So the key insight in all of the work that we did was figuring out information from the way in which the cars ultimately parked on the street. So what we do is make this much more formal in our article. So let me just give you sort of the key highlights of it. So what I'm going to do is I'm going to define the map O, that you input a unit Fubini ranking, and the output is a permutation, which is good because we want some bijections between things that are permutations and things that are unit Fubini rankings. And the way that I do that is I input this unit Fubini ranking, and I get a permutation that denotes the way in which the car's parked. So I write that again in one-line notation, and I just keep track of who parked where. So more precisely, if you tell me pi j equals I, what that means is that car I was the jth car parked on the street. So then what I do is you give me a permutation, and I can then find all of the unit Fubini rankings which park the cars in that order. And so that's what we call the fiber of the outcome map for that particular permutation. All right, so now that we have the main ideas, let's tie this to the ascent set in the theorem. So if I have, again, this permutation, I look at places where from one index to the next, the value in the permutation increases. So that's my ascent set. And then what we were able to prove was that I can give a complete characterization of the elements that park the cars in the order pi by keeping track of subsets of the ascent set of pi. Now notice that there's a pi inverse here. So that's actually important. So pi is the way in which the cars park. Pi inverse is the unique permutation that is a Fubini ranking, which parks the cars in order pi. All right, and I'm going to take subsets I of the ascent set of pi consisting of non-consecutive entries. And remember, as soon as you take non-consecutive entries from a set, you're looking at Fibonacci number many of these. And then this delta of I, with this subset I, is going to decrease values, I plus 1 to I, in pi inverse whenever I is an element of the subset I. Okay, I know, super technical, but let's just go ahead and do an example. And I hope that that kind of puts all the pieces together. Because my question is always like, okay, wait, what? So what do we do? Okay, so here's how we do it. You fix the permutation. So this is either, the parking order, and it's going to become the minimal element in my Boolean. Okay, so that's the key thing here. So pi is going to be the minimal element in my Boolean. So what I'm going to do is I'm going to think about all of the elements in unit Fubini rankings, which park the cars in this order. To do that, that's the same thing as finding the fiber of that map. To do that, I compute the ascent set of the permutation. So let's look at the ascent set. Well, I increase right at the beginning, so I know ascent includes 1. I then decrease, so not a 2. I increase, so there's a 3. I decrease, and then I increase. So my ascend set is 1, 3, and 5. Now what I do is I find all possible subsets consisting of non-consecutive integers. And as I noted before, the number of such subsets is always a product of Fibonacci numbers. All right, so what subsets do I make? In this particular case, I'm going to take subsets consisting of non-consecutive values from the set 1, 3, and 5. And in fact, I can take any subset because there's no consecutiveness happening to begin with. So in other cases, it gets a little bit more complicated. But in this case, I see these 8 different subsets. Notice that that's coming from a Fibonacci, the third one, times another one, times another one. So that gives me 2 cubed, which is 8. Now what I do is I compute pi inverse. And that's, again, the unique permutation that parks the cars in order pi. Then I have to compute this delta I for pi inverse over all possible subsets I. We prove in our paper that the result of that gives you, first, always a unit Fubini ranking, and second, it constructs all of them. So let's just test here. So if I put in the empty set, that means do nothing to that permutation. All right, so we get this one. And notice that that has 6 distinct ranks. Great. Now I look at the one where I put the subset that consists of a single 1, and I'm going to look for a 2, and I'm going to bump it down to a 1. That's what this map delta does. Oh, something happened here in my slide. Okay, here we go. So it took the 2 that you see here, and it bumped it down to a 1. Now I end up taking the next subset, which consists of a 3. And then what I'm going to do is I'm going to take a 4, and I'm going to bump that down to a 3. There's only one 4. So then the result ends up being, let's see. Oh, something is happening. Give me 1 second. I don't know why that clicked off of what I was doing. There we go. So I bumped the 4 down to a 3. So I'm right there. And now I'm going to bump the 6 down to a 5. So this 6 gets down to a 5. Now I do both the 1 and the 3, which means bump a 2 down to a 1, bump the 4 down to a 3. So there's this one. And then I do 1, 5. So it bumps a 2 down to a 1, a 6 down to a 5. I do 3, 5. That bumps a 4 down to a 3, a 6 down to a 5. And then I do the largest set that I found, which is 1, 3, 5. So that bumps a 2 down to a 1, a 4 to a 3, a 6 to a 5. So you do all of this. And what it tells you is that all of these are the unit Fubini rankings that park the cars in order pi. Well, that's great. Oh, this is doing it again. I'm sorry. There we go. So this constructs all of those elements. And what that tells me is that now there are 8, so notice there were 8 subsets. There are 8 Boolean intervals inside of the weak order of S6 that have the minimal element that we started with, which was that fixed pi, which was 4, 5, 1, 6, 2, 3. And if you notice, there was a single B3 that we saw at the beginning. And in fact, you can start, kind of highlighting. So this little dot right there is the permutation that we started with, which also maps to the inverse. So anyways, kind of technical, but it allows you to do this enumerative count, which was the big takeaway. So let me just go back to the statement of the main result. So again, the key insight, which doesn't appear in any part of this statement, is that really we were able to give this result by utilizing all of this information coming from the outcome map of unit Fubini rankings. So all of our proofs were going over into that world and pulling back all of the information through this wonderful bijection that we were able to uncover of these objects. And so I think this is one of the things that I love the most about combinatorics, that, when we were studying unit Fubini rankings, we had no idea that we were creating the tools that we needed to solve a completely different problem in a very wonderful way. So you might ask, what's next? So that worked. That was great. Can you do it again? And that's exactly what we're hopeful for. So we're hoping that we can utilize this idea of unit Fubini rankings, possibly with a little bit of a twist or maybe a little generalization, to maybe enumerate Boolean intervals either in the strong Bruja order or maybe even weak orders for other Coxeter systems. So we posed this problem in our article, and we're happy to think more with other folks about this if you're interested in this work. So the main question would be, how many Boolean intervals are there in the weak order of the hyperoctahedral group, so type B Coxeter group, that have a minimal element pi, and again, arbitrary maximal element W? And so this is a question that we're actively thinking about. So please, 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 if you're interested in collaborating with us, let me just tell you that our research group has a lot of fun. We laugh a lot and really just enjoy each other's company. And so it's been wonderful to share this story with you. So I will end with this thank you slide, which of course, this thing is giving me some problems here. But I have two QR codes in case you're interested in learning more about this. So on the left is the archive preprint, and on the right is my website, which also has a lot of other parking function work if that's something that you're interested in learning more about. But shoot me an email if you have questions. I'm also happy to take questions now. But like I said, always looking for fun people to collaborate and do some cool math with.
Thank you, Pamela. Is there any question for Pamela or any comment?
Pamela,
Yes,
I'm sorry, in English or Spanish?
como tú quieras, tú decide.
Well, in English maybe. Yeah,
Okay.
well, it's really easy question, honestly. You define the order, the weak order, order, using the sense of a permutation, right?
Mhm.
There is a version using the ascents, it's like order dual or something.
Oh, I should
You
tell
could-
you that I am not a POSET person. This is the first project. Well, okay, there's been a few. So if you ask me stuff about the weak order, I'm going to be like, where's Jennifer? She's the expert. But my guess is yes, right? Because if you're doing the ascents,
Yes.
that's the mirror of taking the descent set. So I don't think you get anything new.
Okay.
That's my intuition, right? They behave so nicely when, at least when you're like in permutation world.
Yes, yeah, basically because there is a really relation between the ascent and descent, and when you define this order, I think, looks nice.
Yeah, no, it's very well studied set of objects. And
Yeah.
but like I said, I've been working on more the parking function stuff. So it was really, really awesome to have Jennifer on the team who said, wait a minute, this feels like it has something to do with this weak Bruja order. And so this is how we kind of connected the two ideas, and we're able to use all of the tools from parking function to answer this research question about, these weak Bruja order and the Boolean intervals line therein.
Okay, perfect. Thank you very
Yeah.
much. Amazing talk. Amazing.
Yeah, thank you.
Thank you.
Another comment or question for Pamela?
Hi, hello.
Hi.
Hi. Thanks, Pamela, for this interesting and fascinating talk. And I also like works with lattices and how this theory compares to other areas of the mathematics. So I would like to ask do you know if it's possible to study these Boolean intervals in a more general case where you instead of think of Boolean conditions, maybe modular conditions on the lattice or something like that. I mean, as I understand, a Boolean interval is isomorphic to the posets of a some set with the inclusion, right?
Correct, correct. Yeah, so
Thank
we
you.
were, in this project, we were very specific about looking for that kind of interval, so that that interval had exactly that property, that it looked like a Boolean poset. You,
Yeah.
of course, could look for other things. And I think I was going to just put up the article again by Bridget, because what I would do is I would look up her website. You know, Bridget Tenner has this great website, has all her publications. She also keeps track of pattern avoidance and there's lots of good stuff on her website, because I know she is one of the experts on this area. So really looking at other kinds of posets sitting inside of either the weak order or the, you know, strong Bruja order. She would be my first stop to see what other things people have uncovered. And if you saw, her results really helped us in determining, you know, how to generalize, because she had that really beautiful result that a Boolean interval or a Boolean poset would be an interval, provided that there was this, you could write, you know, the minimal element inverse times the maximal as a product of commuting generators. And so she gave us sort of a roadmap. We were able to use that to, you know, at the end, push the theorem through. So I would absolutely check out all of the wonderful work that she's doing.
Is there another question for Pamela?
Okay, thank you so much for your kind answer. Thank you.
Yeah, you're welcome.
I have two questions, Pamela. Is it possible to study these kind of problems or permutations avoiding a given pattern? You take all the symmetric group, but for example, if you take, I don't know, the permutations avoiding pattern 1, 2, 3, or something like that, is possible to study these kind of problems over these restrictions?
I would say yes. And I bet you the numbers line up really nicely. Like you could use our result, restrict. So instead of looking at the whole Bruja, right, the whole weak order, you could just restrict to the permutations that have that particular pattern. And I guess you use this, maybe you define the same cover relation so that you can get from, you know, tau to sigma applying an SI, where the I comes from the descent of sigma. So I think you can play the exact same game. I don't know the literature well enough, again, to kind of know what has been done. But once you restrict to that set, I think you could use our result to see what is sort of left over. Like, is there enough permutations left over once you restrict that they avoid a certain pattern to find Boolean? Or maybe, you know, maybe you lose all of the Boolean intervals because you're so restrictive in the kind of pattern that you have. So that might be really interesting. Like, is there a class of pattern avoidant permutations for which you can't find Booleans, or the number of Booleans is really much, much smaller than what we're seeing as a product of Fibonacci?
Okay. And my second question is, do you know, or is there any Q analog of the parking functions? I mean, you know that in set partition are Q analogs in permutations, etc. In parking functions?
Yeah, there's definitely some stuff that people have done trying to count certain properties. The ones I've seen is much more for like statistics purposes. So things that have been done, you know, you think about parking functions and enumerating them based on the number of lucky cars. So say, for example, right, like you have a permutation, then every car is lucky. But if you have the all ones vector, then only the first car is lucky. And so there's this really beautiful result of Gessel and So, who give you this polynomial you know, version of that, so that you can enumerate all of them based on how lucky they are. There's also work with displacement. So you can think about the number of spots the cars have to traverse to finally find parking. So the distance between where they wanted to park to where they actually parked. And so there is also a Q analog version of that where they consider displacement. And I think there's a lot in a recent article by Stanley and May. So I would look at Richard and May's work, because they've done a lot recently. Like there was a paper this past summer that came out. So that might be my first stop, because I think they also do a really good job at like summarizing some of the past results.
Okay, nice. Okay, is there another question for Pamela?
There is a question in the chat.
Oops, where I can see the chat. Let me see. Okay, Pamela, could you say more about applying these techniques to the strong Bruhat order?
Yeah. So when I think about the strong Bruja order, so as I understand it, you take sort of the reduced words and then you're seeing, and I don't even think they have to be consecutive. You just kind of find a substring that lies inside of there. That's a reduced word for another. And so that's how you define the cover relations. And we don't know if our techniques are going to work. That's just the honest truth. They happen to have worked in this instance. And our hope is that we might be able to tweak something to be able to use that in the strong Bruja order. But, we finished this paper, you can see here June of this year, and we were starting to work on other things. So we're hoping that we can, do something with it, because I think, it hasn't been the case that when a technique works one time, anytime that I do things with parking functions, it doesn't work again. They seem to have some really nice structure, and this outcome map has helped us in so many of the projects that we've done. So I would absolutely not be surprised if we can adapt the technique to say something about maybe Boolean intervals in the strong Bruja. But again, we haven't actually done it. So I might eat my words and come back, and tell you that it failed. But like I say to, my students, I'm like, we might fail, but we're not failures. So we'll just keep trying.
Okay, in the chat, is there another question? So Boolean intervals are related to musical chairs?
Oh, I have no idea. Are they related to musical chairs? Like the game you play as a kid? The music turns off and somebody falls?
A new problem for you.
There you go. Oh, don't start. That might be the next problem.
Okay, another question for Pamela. Okay, thank you so much, Pamela, by accepting the invitation to this conference.
No, thank you all again for putting this together. It's been lovely.
Thank you.
Okay, thank you, Jose Luis, for your support. And thank you, Pamela, for accepting our invitation. Your work inspired many young mathematicians and especially many women mathematicians in the world. And thank you for this last talk of this conference.
Thank you.
Okay, this was the last talk. And this means that it's time to say goodbye to this conference. But first, I want to thank all of you for attending this event. Our main objective was to bring high-level mathematician lecture to many professors, graduate students, undergraduate students around the world. In particular, I'm very happy that the students at my university feel inspired by all the works that were present at this event. And they are here behind my back. And thanks, guys, for attending this conference. This work is thinking of you and your future. Let me say this in Spanish, because I think this is important. Estoy muy contenta porque los estudiantes de mi universidad se han sentido inspirados por todos los trabajos que se presentaron en esta conferencia. Ellos están aquí atrás de mí. Y quiero decirles muchas gracias, chicos, por atender estas conferencias. Este trabajo que hacemos es pensando en ustedes y en su futuro. Also, I want to thank the scientific board, the invited speakers, the ICM AM team, and also thanks to Arturo Tapia. All of you are already part of the ICM AM community. And let me say some numbers. In each talk, we had around 40 attendees, and every day more than 300 views on YouTube. And this is important for us because it's a motivation to continue working on this project. And I really hope that this experience has been very good for all of you. Now, I will pass the word to the other members of the organizing committee. And first, Marlisha Sandoval Miranda.
Well, thank you so much, Yuriko. Thank you, Pamela, and everyone. I will say some words. Their colleagues, students, hosts, scientific committee, ICMAC, ICMAC, Latin America Board, sorry, Communication Technical Support Office from the CBI WAM Iztapalapa, and all the participants who had been accompanying us these 3 days of talks on topics of high interest in algebra, combinatorics, and theory of numbers, number theory. Thank you very much for making this event possible. For all of us, these 3 days have been enriching to help unite us as mathematicians in Latin America and around the world in a more cohesive community. By the way, tomorrow, our university, UAM Iztapalapa, Universidad Autónoma Metropolitana in Mexico, is celebrating 49 years since its foundation. And it is enriching that with this event, we can contribute to the development of our university and its presence in Latin America and internationally. From the UAM Iztapalapa and the Tardes de Café y Algebra, a seminar algebra in Spanish that emerged in 2019. We thank everybody, and hope that this is the first of many editions of events like this. So thank you so much. Muchas gracias a todos. Felicitaciones.
Thank you, Marlisha. Now we will listen to John Caicedo.
Well, dear all, today I have the opportunity to speak to you at the closing of the ICMAM Latin America Satellite Conference on Algebra, Combinatorics, and Number Theory 2023. And I can only say you thank you. Thank you to the participants who signed from different parts of the world. Thanks to the scientific board for their wonderful recommendations. Thanks to the speaker for taking time out of their obligations to prepare interesting talks. And finally, thanks to my colleagues on the organizing committee for their hard work. I hope this doesn't just stop here. The idea is to keep working on creating a space where everyone can learn while feeling welcome and comfortable. The idea is to create a mathematical community full of equity, respect, equality, and inclusion. I thank the directors of ICMAM Latin America for allowing us to organize this Saturday conference. And in particular, I want to thank Duvan Cardona for his constant support and motivation. No being anymore, it's a good day, hoping to meet you in the future. Let us always continue fighting for our dreams, because how we say in Colombia, pa' atrás ni pa' tomar impulso. Thank you very much.
Thank you, John. Now we will listen to Duvan Cardona.
Okay, so thank you very much. Please, maybe let me share the screen to give you maybe a general perspective about our organization. So, can you see my screen?
It's okay.
Okay, well, so, okay, so in this closing ceremony for this very nice conference, I would like to maybe to say some words about our organization.
I'm sorry, Duvan. Your screen is not clear.
Yeah, it's black. I don't know if it's a problem or something.
Bueno, muy bien. Gracias. Okay, so I will try again. Okay, so can you see my screen?
Yes.
Yes. Mhm.
Okay. Okay, can you see the, Okay, can you see the first slide, closing ceremony?
Yes, everything is okay.
Okay, so thank you very much to all the participants of this conference. You know, mathematics only grow if you find a community where you share your ideas. So let me share with you briefly some aspects about our organization, how we born, our current projects, and maybe let me emphasize about our future challenges. So first of all, I want to say thanks to this very young team of mathematicians, to Yuriko Pitones, to John Vladimir Caicedo, to Marlicha Sandoval, and to Luis Agustin Cárdenas. When they start this initiative, some international societies even were very interested in this conference. Even here you can see the newsletter of the Belgian Mathematical Society, the version of September, dedicate some space of this newsletter to show the announcements about this conference and also our activities in ECMA in Latin America. So I would like to invite to the participants to open your microphones and to offer a clap for this very nice job that this organizer did with this conference. Entonces, los invito a abrir los micrófonos y a dar un aplauso a este equipo tan maravilloso. Very well. So, of course, I would like to say thanks to the scientific committee and to our team of speakers. We have the help of very nice people here, very nice mathematicians that were very supportive with our conference. Thanks to Matilde, thanks to José Luis Ramírez, to Sergio López, to Felipe Rincor, to Luis Núñez, to Carolina Benedetti, to Sonia Trepode, to Martina Junque, and to José Samper, who really were behind in the invitation of all these very nice, speakers that we had. This was very inspiring. I know that maybe the community in algebra, combinatorics, and number theory really appreciate of these talks. So coming back to maybe to share with you how we born. We born 3 years ago in Cali, Colombia in 2020 in the pandemic time. In that time, the idea was to just to organize one conference. You can see here the list of speakers. All of us were maybe PhD students, maybe postdocs doing mathematics around the world. And the idea was to create one scenario to share some mathematical ideas. And somehow we had in that moment the idea to open the virtual participation only for Colombia, but also for other Latin American countries. And that was a very successful idea because we count with the participation of 12 countries. So that was very interesting. We saw the potential that have somehow this kind of a scenario in the setting of digital platforms. So the past year, looking at the potential that these kind of ideas have, we organized a big conference that we call ECMA Latin America Conference 2022. That was very nice because with the idea of having one scientific committee, we invite very nice mathematicians that at the same time provide some inspiration for young Latin American mathematicians like Terry Tao and Simon Donaldson, who are very known mathematicians because they were aware with the Fields Medal, and also other mathematicians like Michael Ruchansky, Enrique Suazua, Carlos Koenig, David dos Santos Ferreira, Tatiana Toro, and Harald Helgoff. So it was very interesting. You can see here also between the speakers to Christine Lauter that also was related with this conference. Even just let me mention, for example, the participation of Harald Helgoff, who is, an authority in the field of number theory, was possible only with the help of Emmanuel Carneiro, who also was a speaker in this conference. So this really was a very nice initiative. So We understand the potential that this idea have, the idea of having one scientific board, the idea of collaborating with young mathematicians. And then this year, we have the idea of growing, not only like a, like a conference, but we wanted to create something, maybe an organization, one academic organization that we call now the ECMA in Latin America. Now we have some goals. Our goal, for example, is to work for the visibility of the mathematical research in our region. So part of this work has been possible because we have with us very young mathematicians like Yuriko Pitones from Mexico, like Marlicha Sandoval also from Mexico, also some Colombian mathematicians that are helping in this project, like Bienvenido Barraza and Jairo Martinez, and some people that from the beginning were related with this opportunity. So now, when always young people become to your group, young people came with very nice ideas. For example, someone from our group proposed to create one disclosure commission, and here you can see the team that is working for this initiative. Now we have somehow for the interaction with social network, we have one press officer. And for example, Yuriko Pitones has now the initiative of creating one commission about equity of gender, which is something that is, of course, very important. It's very nice, for example, to see that from the past year, let me mention, we in the scientific board, we just have somehow 7 mathematicians, and now because our activities are growing and growing, now we have with us the support of 40 mathematicians that are working in the construction of this conference and in the construction of this scenario. So something important is that all this has been possible because we get the support of 3 international societies: the International Society for Analysis, His Application and Computation, which is present in Europe, in Asia, and in America, the Sociedad Colombiana de Matemáticas, the Sociedad Matemática Mexicana, the Universidad del Valle, the Universidad Autónoma Metropolitana, the Ghent Analysis and PD Center, and the Belgian Research Foundation, FWO. So all this was more or less presenting the members and of our organization and all the people that have been integrating this team. But then let me maybe share some announcement about our future activities. So we will have, next conference will be in October, one conference in analysis and partial differential equation. You can see here. There we will have also, like in this conference, very inspiring mathematicians, like this mathematician, Charles Pfefferman, who is very well known because he won the Fields Medal in 1978, and many other mathematicians that in some way or in another inspire our young generations. So we also will have the Satellite Conference on data science and machine learning, maybe related with this conference on algebra, number theory, and combinatorics, because data science is related somehow with cryptography and machine learning with coding theory. So this is something interesting. It's interesting also to see that the organizing committee now is not only from academia, it's also working, for example, in insurance companies like Alliance, which is, the insurance companies that support the Olympic Games and the Paralympic Games also. And this is somehow very interesting. So one of the main goals of ECMA in Latin America is to work also for the, the visibility of the mathematical research of women in Latin America. So it's my pleasure, I am very happy to announce that in our future, we will have this initiative, which will be a book that Yuriko Pitones and Karina Navarro Gonzalez, that are both members of our project, will edit. These 2 young women mathematicians will be the editors of one Springer volume, and the idea will be to receive contributions of women's mathematicians from Latin America irrespective of the idea. All the ideas are welcome. So soon you will receive invitation of these two mathematicians for accepting contributions. So also we have similar somehow initiatives in other fields, not mathematics, of course, but also in other fields, analysis and partial differential equations. And the idea in the future is to incorporate maybe more volumes that allow us to have a general perspective about the research in Latin America in different fields. So where we are going, just let me say that we want to put the mathematical research in perspective, not only in Latin America, but also in other societies. For me, it's a pleasure to say that the ECMA in Latin America, with the help of all these people, with all these board members, with the help of many people related with our activities, we participate competing with several countries, representing to Colombia in one competition about who country will organize ISAAC, which is the main somehow Congress of analysis that organize the International Society for Analysis, Application, and Computations. So it was very nice. I was very happy when I was informed that Colombia, in representation of represented by ECMA in Latin America, will organize this conference in 2029 in Barranquilla, Colombia. So this shows how much we are working, let's say, with the support of international societies to take different goals. Not only somehow, okay, organizing conferences is very nice. We are very happy to hear mathematicians and so on, but we want more. We want to have visibility of our young generation. We have to include somehow to present to the world a perspective about the research that we are doing in Latin America, and we want to somehow represent also our countries in different important events like this of ISAAC. So just to finalize, sorry if I went long, I want to say thank you to Mexico and Colombia, who was in charge of this, were in charge of this conference. So thank you very much for your support.
Thank you.
Okay, so I will pass the word to Yuriko Pitones.
So thank you so much for your speak, for the announcement, Duban. And I think it's time to say goodbye, and thanks everyone to attend this conference. We wait for you for the next edition to this conference on algebra, combinatorics, and number theory. Was a pleasure for me. Thank you, team.
Thank you. Bye-bye.